Hello and welcome to the first video of the Introduction to Computer Programming tutorial series. My name is Kevin, and to my right I have...
Bryan. We wanted to create this video series so that you can basically hear a conversation about software development, what you're going to find, what's valuable to know, what you should focus on, what to expect. And these are all things that we've learned over the last 10 years as software developers.
And the main reason we wanted to do this is because Bryan and I had no one to do this for us.
That's true.
Neither one of our parents were in the field. We really didn't have anybody.
All of your classmates are age mates, so they don't have any more experience than you do.
And
your teachers have never worked a real job ever
yeah,
in their
that's
life.
true. Because they just work in the university
Yeah, they're
system.
stuck in academia. If you can't do, you teach.
Yeah, exactly. So we never really had that advantage. So we stepped into the workforce with one expectation and completely got blindsided.
Mm-hmm.
So hopefully we can help some of you guys that are kind of moving in that direction manage your expectations and help you get a good start in the field of software development. And also to define whether this is something that you want to do in the first place.
Right. These are a couple things that are necessary skills to be a software developer, at least a halfway decent one. You have to be able to solve problems. And you have to be able to solve problems well. You have to be able to solve problems fast. You probably didn't start getting into this without that skill set, but this is definitely the most important skill that you can have.
Absolutely. Adding to that is the explicit attention to detail, because you need to be able to break down these problems into small parts. One of the more popular methods of software development is the modularity concept, where you have different portions of your code that are specialized doing different functions. Mm-hmm. And the reason why that's important is because you can, if you write your code in that way, you can reuse things. It's easy to support, manage, document, and that sort of thing. So your programming skills and your ability to break down problem solving is a direct link to how good your code, in the end, actually ends up.
Also, if a problem got to you as a software developer, it's probably a problem that was more complicated than somebody else could solve. And a very common approach to that is the conquer and divide. So in order to conquer and divide, you need to divide into smaller parts and be focused on all of the details and moving parts of the problem. But it also means that you need to be able to research, because there's nothing wrong with not knowing.
Absolutely.
When you approach a problem, how to solve it.
Most of the time, you're not going to have a clue at all what you're doing, especially if you're new to the field.
Yeah.
But you need to be able to know, and this is where college comes in handy, because in college you don't learn how to write a lot of the software that you do in the field.
Nor are you taught by your teachers.
Right, but what you do learn is how to research to get the information that you need to know in order to do what you have to do.
Right.
Having that understanding and know where to get the information, know how to use that information, research is key in this industry.
But then again, you're here watching this video, so you probably already got that part.
That's true. You know that we have the best source of information, and that's why you're coming to us.
Exactly. So. Also, even though it sucks, it's horrible, it feels like you're going through somebody else's dirty sock drawer or whatever, the ability to read code you did not write is unfortunately a necessary part of your job.
Especially
when you're new.
Especially when you're new. You new guys are going to have to walk in. You're going to be... The first thing that you're probably going to be given, just to kind of see where you're at, is some mess that somebody left for you.
Right.
Either the guy that quit that you replaced, or just some horrible piece of code that nobody wants to support. And they're just like, we're just giving it to the new guy because none of us want to own this.
Right. So, even though it seems like it'd be faster to write it from scratch, sometimes that's the case. Most of the times, that might be the case at first, but as you learn to read other people's code faster, if the code seems like it's stable enough to run, just read the code, do what you need to do, move on, come back to it if there's time allowed.
And because there's not one programming language, you're going to be running across many different kinds.
Yes.
So when you're given projects where you're taking on code that's already been written, expect to see a lot of languages that span the entire spectrum. So it's important to understand, at least have a basic understanding of as many languages as you can.
Also, you have to be able to take responsibility. Own up to your mistakes, and don't be afraid to make mistakes. You can't learn anything without making a mistake.
Absolutely.
It's just not possible. You can't be so risk-adverse you do nothing, because you won't learn anything. If you don't learn anything, you'll never become valuable.
I brought down an entire production system once.
Or 10 times.
Well...
Or 20 times.
I made a mistake.
I do it like every day.
It was because of that mistake. Just for fun. It was because of that mistake I understood. Oh, okay. Don't do this. And I think for the most part, management is relatively reasonable with, depending on how big of a group you have. But, try to manage your mistakes. Try to do the best you can, but don't be afraid of it. And make sure that when you make a mistake, own it.
Right. Also, another thing is, some people have this saying that they say, greater minds than ours did this project. Greater minds than ours thought of these things, I'm sure. You know, and that's kind of like a manager's way to prevent you from doing something new. You know, it's kind of part of their risk aversion thing. Just because there was greater minds than ours, or whatever the phrase you might think, because people in the past probably knew better, because they'd been there longer, well, the greater minds aren't there now.
Yeah.
So don't be afraid to try something new.
Absolutely not.
There's nothing wrong with it. You are the greater mind. You are somebody else's greater mind when you leave.
Yes.
And so on and so on.
And they left you their project.
Yep.
You are now the greater mind.
Exactly.
Yep.
So don't be afraid to try something new.
So we kind of went over a few things. We want to talk about some of the good things, the benefits. So, although Brian and I, before we got into this professionally, you know, we were just little kids hacking away, building little programs and websites, and we were just little guys in our parents' basement. So we obviously had a passion for this early on. And the main thing that attracted us to this was because it was fun and challenging.
I remember the first time I got a job, you know, like really developing, opposed to just kind of doing, you know, sometimes you do like desktop support kind of stuff, you do kind of whatever sort of bullshit work, or like web development, like very basic HTML kind of stuff. But the first time I started working as, you know, really getting into writing code, I thought to myself, oh my god, I'm getting paid to do this.
Yes!
Like, this is insane. I can't believe they're paying me to do this. So, it's pretty cool.
Yeah, I could definitely relate. I had a very similar experience. Yeah, when one of my first programming gigs was doing websites. So I remember getting checks for that. And I was like, whoa! I do this when I'm bored, and I'm actually getting paid to do this. So this is good stuff.
And you can spend their money on, you know, servers and all sorts of crazy stuff that you never had the ability to buy before. So instead of just having like old laptops with no screens that worked in like an old Dell from the mid '80s to kind of do your stuff on, you know, now you have like a server room. You know, it's awesome. It's really pretty cool.
So that kind of bleeds into the next point here. Is it's very gratifying work. I mean, when you build something, and you know, whether you're building a product, you know, we've worked in different jobs. We've built different types of products, but when you see that product being used and how it benefits the company financially, how it benefits the customer functionally, and also financially, because it saves them time, it saves them money, you definitely feel a great sense that I did something important, I did something good. You know, even though you're there for hire, you did your job, but you did your job well, and the outcome of your, you know, it's not like you're some lawyer that you know, somebody burned themselves on some coffee and you sued an elementary school and you took all their funding away, and that's how you got your money. That's not gratifying. That's disgusting. This is a complete opposite of that.
Right. The role of a software developer is very important. Most businesses wouldn't be able to function without software development.
Most? I think at this point we're at all.
Pretty much, yeah. So it's extremely important. Every industry needs software.
Absolutely. Even if it's just QuickBooks or Microsoft Word, it's necessary.
Mm-hmm. So if there's an industry that you're passionate about, don't focus on the fact that you need to work for a development company or a tech company. Focus on an industry that you're passionate about, and they will have a need for software development, because every industry needs it.
Always a need. Absolute. That's a very good point. You know, we are also very fortunate to be in one of the highest paid in most respected professions. I know the U.S.
Yeah.
You know, I know that when I tell people what I do, a lot of times you get that look.
You read code? That's weird, you know? I'm like, well, I guess, yeah, I suppose. I don't usually think about it that way, but whatever. You also get to work in very creative environments.
Sometimes. Parentheses.
On occasion, you basically will just be working to get a paycheck. You'll be doing what you're told, and just take it as something to put on your resume. It's a stepping stone job, and move on. But generally speaking, you'll always be working in creative environments with other people who are looking to work in creative environments, and other creative people that you can bounce ideas back and forth on.
Being a software developer, you get to have a lot of exposure to a lot of different things. I mean, so if you're writing writing software, you may have to learn a lot about things like databases, libraries for, whether you're running COM objects or that sort of thing, web services, file formats, that kind of stuff.
When some people want to get into computer science, they're kind of offered two options early on. One is going as a computer scientist, as a developer, or as an information technology specialist. And those are two very drastically different paths.
Extremely different.
So IT applications is fixing computers, installing stuff, making sure that they have power. That's applications of information technology. Software development is a different arm. And in that other arm, it spans the gamut of everything technological. I mean, from embedded programming in devices that have to function 200 meters underwater, to hardware that has to work in outer space, to everything. So from the backbone of the internet and how it functions and how to improve on it, to rendering engines for the newest video games.
But think about all the things that you mentioned, and if you're working in these projects, imagine the amount of things that you learn just from being a part of it. You know, just imagine what the NASA engineers that put us in the moon had to go through, and what they walked away with.
Or even the people working on Hubble now. But there's still a lot of software developers working on, you know, all sorts of fun stuff. But it is sometimes challenging, and there are challenges. It's very high pressure. You have to be able to manage stress. You have to be able to think clearly under pressure, and knowing that you must succeed because there's nobody else to succeed for you. The job has to be done.
I don't think you're going to put it another way. Nobody else can succeed for you. No one's going to come up behind you and sweep up your mess. You know, a lot of times when you're given these projects, you're given a specific part. So many people are depending on your part being done.
Yeah, and some industries are definitely life and death as a result of what you do.
That's true.
So it's not only high pressure from, you know, your boss, or high pressure from an arbitrary date and some sort of project management timeline, but it's also, if I can't figure out why this code isn't functioning properly, people aren't going to get their medication. People aren't going to be able to have their fetal monitoring systems activated so that doctors can see how the fetus is, you know, responding to a certain type of drug. Whatever the case is.
Or the Hubble Space Telescope will turn around and start shooting lasers back at the Earth.
Destroying all baboons. I don't know.
Baboons. From this, you do put in a lot of hours. Now, not all jobs do this or require this, but there are many that do. Research time in many cases will exceed the amount of time that you spend developing your projects. And because of this, a lot of time that you have to spend in your personal life is spent thinking about your projects or learning about your projects.
You'll be given some time to do research at work, but not that much.
So
most of the research you're going to do is going to be on your own time.
You're going to have deadlines. And those deadlines don't include research time for the most part.
Yes, right. And that also gets into something we won't get into here, but you know, how to manage project management.
Yeah.
And how to box out your time and how to try to fight for yourself to have time to do research. But generally speaking, you won't get that. Usually they'll expect it to be done in 2 hours when you say it takes 2 weeks. And the job is sedentary. I mean, unless your chair is replaced with a treadmill and you have your computer propped up on there, or you're one of those like Bluetooth iPad assholes at Starbucks, you know, like pacing back and forth, you're going to just be sitting and just like your eyes are going to be bleeding.
Yes.
And your fingers are going to be numb. You're just going to be sitting there cracking at something. In order to be able to keep focused for long spans of time, you should be physically fit.
To the best of your abilities.
Yeah. So try to exercise. And also doing physical activities after work helps you break out of the programming mentality.
Otherwise, you never leave work.
Right.
And you're always stuck in work.
Never relax.
And that stress level can completely consume you.
Yeah. And it's a natural situation to get into.
It's a very, very easy situation to fall into. You know, having said all that, you do need to try to at least somehow get physical activity in your lifestyle, knowing that this is a very exhausting field. And we're not even talking about physically exhausting. We're talking about mentally exhausting, where you'll spend a lot of time working, and at the end of the day, you just can't think anymore. You don't feel like doing anything. You want to go home, you want to turn the TV on, you want to watch Family Guy or something, and just veg out and not think. But, you know, even though that's very easy to fall into, it's try to go for a jog. If you have a dog, take him for a walk, that kind of thing.
Yeah.
And then watch Family Guy.
What should you expect in the workforce? Regardless of experience, there's going to be people who know more than you do, and there's going to be people who don't know anything. If you're in a situation where you think that you're the all-knowing, all-powerful oracle of the company, and all others bow before you because you're a rock star, there will be somebody else who comes along who knows more than you will. It's inevitable. And that's not a bad thing. You should always be encouraging others who know less than you to know more. Don't be cocky. Don't make it a competition. Just encourage everybody to know as much as possible for
Because
the benefit of the group.
Because a development team is like a sports team in that you want the guy next to you to be as talented, if not more talented than you. Because outside of your group, the only thing that everybody in the company knows is that the development team is good or the development team is bad. They don't know that you as an individual are good or bad. That's your manager's job. But it's your responsibility at your level to make sure that everybody is good.
And most problems and projects will require more than you.
Yes.
Most difficult problems and most problems that are worth bragging about accomplishing are going to require many people to solve, no matter how good you are.
And and also when you divvy out assignments, you need to be able to depend on everybody getting their work done when they're supposed to have it done.
Right. So you want them to be as good as they can be. So you have a dependable, reliable team to lean on when you need to.
And in many cases, when you come into a new organization, there is a short grace period of time. Now, this isn't for all places, but like 3 to 6 months usually to get acclimated into their environment.
Right. So usually you're not expected to hit the ground running when you come into an organization. It's not, I know this language and I'm familiar with this kind of thing, and you get the job and day one you're in there writing the code. You need to learn the process, the development life cycle, the environments, where code is stored, what the style is people use, how people do documentation, whatever the case is. It takes a while to get acclimated to those kind of things, let alone to just get acclimated to the type of work that you're going to be doing.
And make sure that you don't lie about what you know. That's a big thing. Because, whether you're in a job interview or in a situation where you're given an assignment and you're asked, do you know X, Y, Z? Well, if you don't know why, make sure that you say that you don't know why. But also be enthusiastic about the opportunity to learn and understand why.
Right. Companies want you to invest in you because you will be a return on the investment. If you show that you're enthusiastic and excited about learning something, the companies will encourage you to do that. But if you say you know something, you'll be expected to know it. And that will just prove your incompetence.
And when you're a professional, for the most part, no one's going to be sitting there holding your hand. You're going to be given an assignment, and you're going to be given a date, and the expectation is you're going to be done at this date. And then there are no ifs, ands, or buts. Things you learn to live with. Oh, goodness. Developer time is not 9 to 5, Brian.
That's true.
Did you know that?
No.
How many times have you woken up in the middle of the night with an idea that you had to just get up and work on?
Twice.
Only twice.
Just all the time.
That is a lie.
All the time.
I know that's because I know that I have
Usually
spoken
it's every
to you.
hour on the hour, all night long. So these are things that you learn to live with. Everything's not ideal in this industry. Your time is not 9 to 5.
No, absolutely not.
You may clock in 9 to 5, but you will be solving a problem at 3 in the morning, at 8 at night, at 6 in the morning.
Yep.
Anytime.
Yep. Yes, and whether you're actually on the job doing it, or whether you're out at a bar having a drink doing it, whether you're sitting in bed at night, inspiration will strike you at the most inopportune times. This is something that you're going to have to be aware of, and over time, you just learn to live with it. It's just a part of it. You're in a creative field, it's sort of almost like musicians will have this, where they'll have like a recorder next to their bed.
Right.
Or if they're dreaming about a song, they'll wake up and they'll play it.
Yeah.
It's a very similar type of thing.
So your work will come home with you.
Absolutely.
And not only is it that you'll be inspired at strange times, but you do have to learn constantly. It kind of goes back to what we were talking about research. Technology is constantly changing.
Always.
So you always have to change the technology. The only way you can do that is to learn. And you probably won't have enough time on the job to learn. Not only are you going to be thinking about your work from time to time, but you're also going to be learning about your field.
And those people that don't take the time to follow technology very quickly outdate themselves and make themselves irrelevant.
Yeah.
So you definitely decrease your value.
Also, you have to understand everything about your projects.
Oh, yeah.
In order to deliver a good product, you have to understand what's being delivered. Because most times, the person who's giving you the requirements won't fully understand the requirements they give you.
They're not a tech person.
Right.
Yes, that is true.
So you have to be able to make some decisions for them and keep them in the loop, but you still have to be able to translate that down to a technical level. And the only way you can do that is to understand fully your projects. That might require after-hour learning time as well.
Yeah, and a lot of times in requirement collecting exercises, I know you and I have fallen victim to those miscommunications where information is just not given correctly, and you're forced to make assumptions that in some cases are just flat wrong. Mm-hmm. And it's not your fault. You just made an assumption because there was information was not given to
Yeah.
you, or information was actually given to you that was wrong,
Right.
which happens too. So that's just something that you just have to learn to live with.
You do the best you can. You try to follow up with the stakeholders as often as you can. But the industry of software development is very diverse. In some companies that do certain types of things, you might see certain constraints on demographics, but you probably won't find that as much in software development, other than that it's kind of sexist. It's a male-dominated, generally, industry, but that doesn't mean that it's anti-female.
Yeah.
Most cases when I've seen a female developer apply for a job, they usually have a higher probability of getting the job because they offer a unique point of view.
Mm-hmm.
And most development groups are always looking for more unique points of views.
Mm-hmm.
And finding a female developer is few and far between. So if you are a female and you're looking to develop, you're extremely valuable just by the nature that you're a female. But that said, it is a male-dominated industry. Also, most people in this industry will tend to be more on the nerdy side, so they won't be quite so good old boys club jockish,
Right. Yeah, right.
putting down
Yeah.
the girl. So you probably won't deal with a lot of sexual harassment. You probably won't deal with a lot of sexism, but it is a male-dominated industry.
If anything, they don't know how to deal with females.
Right, so you'll probably have more powerful over the groups because
Yeah.
they'll just cower in fear that you're a female.
Well, it's funny phenomena you just mentioned, because I can recall, you and I talked about this back in college, that you remember like the computer science, like the introduction to computer science course. Maybe it was like, I don't know, like mostly guys, but a good portion of females. But as you went further along the curriculum, less girls, and to the point where we graduated, 0 girls.
Right, and it's definitely not a matter of female competency. I think it may be more of what the expectations girls have. I think part of it also is that all technology tends to be geared towards guys. I mean, go to a game store. How many games that have cutting edge graphics and cutting edge technology are cutting edge in ways to shoot somebody or to race a car? So they're definitely geared towards the male soldier, the male race car driver.
Right.
So the video game industry but it's
one thing to keep in mind. At one point, nursing was female dominated.
and now
It's
changing.
not.
Right.
And you know what? Over time, this trend will also be the same as software development. Brian and I welcome this. I mean, this is a good thing.
Yeah.
But you don't only deal with gender issues. You deal with ages. You deal with cultures. I mean, a lot of times,
it's very culturally diverse and it's very age diverse.
The age diverse thing it can be very frustrating, especially for the young guys and gals coming out with the most cutting edge technology that they just came from training school or college with, where you got a chance to see all the great, amazing stuff that's out, and you get to toy with it, and then you go to a place that's a lot more conservative, where you have guys that are more set in their ways, they're a little bit older, they use older technology, they don't want to move forward, so that kind of thing gets frustrating.
Right. A lot of places you'll run into older developers who won't even know what object-oriented programming is.
Or will complete, like, for example...
Or refuse to accept that it's of any value.
Or refuse to accept the language as a legitimate language.
That's true.
Like some web guys will say Visual Basic is the language of the web.
Right.
But more and more that's changing. But maybe in 1994 or 93, when that was right.
For 2 years.
But that was right. But you know what? I'm sorry, dude. It's just not moving. The trend is not moving in that direction.
So don't fight this because you will kill yourself.
You will have scars in your face from banging your head up against the wall.
So just embrace it. Try not to be confrontational and cause dividing lines within a department, but just try to embrace it.
But also in companies where they have gone through some outsourcing, you are going to be probably working with people that are literally located in different countries. Mm-hmm. So not only are you going to be dealing with cultural differences within your organization, but you may be having to interact with people that the language that you speak is their second language. So,
That's true.
So there are going to be some language differences that you have to work through, and that requires patience and understanding.
Right. Some other things you'll have to learn to live with is how to propose on new ideas without forcing them. This can kind of turn around and bite you if you don't accept this.
I know Brian and I in our professional lives have seen this a lot, where managers tend to be very risk averse, and they don't want you and your hotshot ways to change what currently exists. Mm-hmm. They have their idea of what things are supposed to be like, and if you come in with a new idea, sometimes they just shoot you down.
Yeah.
And you need to be able to be emotionally strong enough to sit down with a manager or a senior engineer and have spent hours putting a proposal together and have them look you dead in the eye and say, no. The fact of the matter is, your idea went across, and maybe later on they will see that, oh, maybe this idea has value, and later on we'll come to it.
And senior managers do not want to be undermined, but they should be.
If you're right, they will eventually realize it. I know that we've seen this before. And the best way to be right, the best way in the world to be right, is to let someone else do it and fail.
And I might be wrong about this, but I'm still okay with saying I told you so. Because otherwise...
Make sure you document it, though. Make sure that you document it.
Because people will take credit for your ideas.
Oh, yeah. Yes.
So, and magically, somebody will come up to you and explain something that you know for damn well sure that you explained to them 2 weeks ago.
Like, didn't we just have a
their
meeting?
Idea failed.
We just had a meeting about this. I gave you a PowerPoint presentation in an email
because
that
you didn't
explains
feel like
this.
reading the text paper. So people will try to take credit for your ideas. There's nothing wrong with saying, sticking to the fact that it was your idea, but it'll happen. It's bound to happen. People will take credit for your ideas. Learn to deal with it as best you can.
I think this last point is one of the most important points that we came up with during this entire presentation.
I agree.
Not every day is a victory. And for those of you that have been in the field, this is probably one of the truest things that you've heard. And for those of you going into the field, this is a very important thing for you to hear, because you're going to leave work sometimes feeling like a failure because you spent all day trying to get this to work or trying to do this, do this, do this. And sometimes you just leave after working a long day with nothing. Mm-hmm. And I don't want to say that more often than not that happens, but it does happen a fair amount of times.
Yeah. And sometimes you just have to walk away from something. You come back the next day with a fresh pair of eyes, and it's plainly obvious. You solve it, you move on.
Yeah,
so
that is
don't
true.
kill yourself. Just walk away, relax. Don't worry so much about it. Stress will prevent you from being able to access a lot of your brain.
Yeah.
So stay relaxed. You'll stay sharp.
And that's where that inspiration at 3 a.m. is going to hit you. We want to talk about the developer community, because when you are a software developer, you are not an individual. You are a link in a chain. You are part of a community, a group of people that are all basically working together, where everyone to either side of you is trying to help you succeed in what you do, and you have to do the same for them.
And a side note, the developer community didn't always exist, and it wasn't always there. I mean, when we were far younger, when the personal computer just started becoming popular in people's homes and people started developing at home for the first time, resources for development were few and far between.
That's because the internet was still infant, too.
Yeah, but people who had information were not quite so friendly with it and not quite so willing to share it with other people because they felt...
They were academics.
Exactly. And they felt like it would devalue their knowledge.
Yeah.
So if you don't contribute what you know to the developer community, and if you don't try to take an active role in it, the developer community can always return back to something that's not very helpful, like we find in the Apple developer community.
Yes. The Apple development community needs to have... They just need to have a lesson. I don't know. They need help, those people.
I think, it's the smugness.
Yes. So try to take advantage of this. There are a lot, except for Apple, there are a lot of great opportunities out there to learn on message boards. And, we're sitting here making fun of Apple. That's not always the case.
And it's not necessarily Apple's fault. It's just, it seems to be the type of person who tends to develop on Apple equipment.
They seem to have this weird mentality where...
It's the art at Starbucks that happens to be a developer.
Yeah. Yeah. It's the guy that, he has a Mac... And he just sits there at Starbucks, angled so that you can see that he has a Mac. That's the guy that kind of that is not so good.
Yeah.
So he's also the person that thinks that you can't write a virus for Mac.
That's right.
He's one of those people too. So
Apple's immune to viruses.
Yeah.
Apple makes great stuff. Their developer community needs help.
So please take advantage of this, and at every opportunity, please contribute back. In every time that you give back to this community, I promise you're going to get something back, and you're going to get 10 times more back than what you had invested in the community.
Yeah.
So always help other people that need it. Now, but one thing to keep in mind is if you're writing proprietary software, there might be company policies about sharing code, copyrights, and that sort of thing. So before you actually share full code, be aware of your company's policies and that sort of thing.
Yeah. But there are projects out there where you have open source code that's free to use, so you can see what other people are doing. You can see projects people are working on, and some really cutting-edge stuff that's out there that you can look through the code. I mean, Firefox obviously is a very easy example. I believe Chrome is open source as well. I mean, the Linux kernel, pretty much whatever. I mean, you can really get into anything in the open source realm. Inkscape is kind of like Adobe Illustrator. All those kind of projects, you can get the source code and see how they did it. GIMP, yeah.
All that kind of stuff.
If you're interested in graphics processing, there's a lot of stuff out there, and if it has a GNU license, you can use it. If there's code within the project that's helpful for you, you can take that, you can make it your own, you can work it into your project.
And you can change it.
You can change it.
You can use it. Right. You can use it in whether you're developing freeware. I think for the most part, you can also use it in commercial applications that you're selling.
Yeah.
You know.
So it's an invaluable resource, and so it's invaluable for you to use as well as to contribute back to. So development is not a job; it is lifestyle, and always keep an open mind. Your way is not always the only way or the best way.
That is very true.
It probably isn't.
Probably is not.
So the question is, am I still a software developer?
Am I still?
Probably not.
Probably not.
So hopefully you get something out of this. Hopefully this kind of helps you stay focused, helps you stay motivated, helps you to not become demoralized if you happen to be, and gives you a bit more of a perspective of what to expect when you enter the workplace. So that brings us to the end of this discussion of what it means to be a software developer. Yeah. So if you're still interested in software development, after all this, then you probably are a software developer. So that brings us to the end of this video. Thanks for watching. Hello, my name's Brian, and this is Kevin.
Hey.
And this is Introduction to Programming Languages. This will be a relatively fast-paced introduction to basic concepts of programming languages, development concepts, and what you'll generally get exposed to when starting to program.
We're going to just kind of take this from a high level at first, and then as these videos go along, we're going to kind of get a little bit deeper and deeper into the actual gears and switches of this whole thing. The first piece that we want to discuss are the core instructions. What can my computer do for me? It's easy in today's computing world to forget that we see all these wonderful, fun graphics and sounds, but computers really only have very basic things that they actually do. And it's just the manipulation of these things that produce these things that we see and use all the time.
Mm-hmm. Everything that your computer does is essentially based on a series of execution statements of basic math and moving data around and in basic comparison operations. Basic math is just addition, subtraction, multiplication, division. When memory is moved, like a file is copied or loaded into memory, or it's basically just storing and moving data.
So in the process of loading a file, you're storing small pieces of data in the memory registers to walk it through.
Bitwise operations, something and something else, or something or something else.
Yeah, we get to that later, but bitwise operations are just basically logical expressions.
Comparisons, if something is greater than or less than or equivalent to or not equal to, and control flows. So if this happens, then do this. Or once you get to this point in the program, jump over to another point in the program.
Or execute this code while this condition is true, which is the concept of a loop.
So these are the basic things a computer can do. So when you watch a movie on your computer, when you watch Facebook page of somebody telling you that they made a sandwich a minute ago, those are all based on basic math, basic logic. It's just a very complex combination of those very basic functions.
Yep, and all these fun things that we see are just built on top of this. Brian and I also wanted to discuss the two fundamental types of languages. We want to discuss the low and high level languages. The low level languages, even within these, there are subsets. But generally speaking, a low level language is some sort of language that has little to no abstraction from the machine architecture.
It's not human readable. It looks like matrix code. Like it looks like something that you'd really have to get into and really focus on to understand. So it's not necessarily designed to be convenient for people to use, but it is designed to be efficient and relevant for the computer to understand.
Right. It also, low-level languages also technically fall into the machine and switch realm, whereas even before languages existed, all people did was manipulated wires and switches to perform an instruction.
Believe it or not, low-level languages were originally used to be convenient for people, but that was kind of the best that they had, you know. So now we're used to very fluffy languages like Java, but back when computers started, they were just getting this going. But there's also high-level languages with greater abstraction, more human-readable, and the way that the language reads is kind of the way you describe the program. If this happens, then do this while this is happening. It's more of a sentence structure.
So if you kind of also look at this slide, we mentioned that there are language generations. We wanted to kind of put this here without explaining it, but in just 1 second, actually right now, we will take a look at the language generations. Like I was kind of just describing a minute ago about the machine-level languages, the low-level languages, they kind of sit within these first and second generation, and they kind of bleed into each other. In the first generation of languages, this was around the time that digital computers were becoming in full use. From the 1930s to about the 1950s, you were seeing a lot of things that were vendor-specific types of instructions that were either manipulating cables or switches, or machine code such as binary or assembly language in order to get a computer to do something. And these were the days where you had to have thick glasses, a pocket protector, and no life in order to work on these machines.
And debugging actually means like killing bugs and cleaning them out of the system, like actual insects.
Yeah.
So second generation is not far from that, but there is a little abstraction from the machine language, and we start seeing this in the 1950s, the 1960s, where you start having some more wide applications of the same systems. So like you were saying, they're more vendor-specific. As machine abstraction began, you could use the same system and apply it in a few different ways.
Right. Also kind of making things a little more industry standard. That kind of started around this time.
Absolutely. So this is where we first start seeing logical operations, and this introduces languages like Fortran, Lisp, COBOL.
In the next couple generations, and actually before we continue, we want to mention that if you look up language generations, you may not see it exactly laid out the way Brian and I did it. We kind of did it the way that we felt that it should be, and not necessarily the way that some people have designated this to be. Because Brian and I were actually kind of heartbroken that so many people believed that modern framework languages belonged in the third generation, when there's an obvious distinction between third generation and modern languages now. When we talk about third generation languages, we talk about the move towards human-friendly languages, in which we started seeing that around the 60s into the 80s, which we saw a much more further abstraction from the structured languages that we were talking about before, like Fortran and COBOL. The momentum was to try to make it so that humans could actually look at a piece of source code and understand what it's doing just by looking at it. We also saw things like the introduction of abstract data types and object-oriented programming, and some of the languages around this time that were coming out was Smart-Talk, which was credited as the first object-oriented language. And then your lower languages like C, which is a low, high-level language, if that makes sense. C++, BASIC, and SQL.
Fourth generation languages are where we start seeing frameworks. Not only are they human-friendly and have a very natural speaking flow to the language, but they also utilize large libraries to perform some of the more complicated functions. So in the fourth generation languages, you will not be so tempted to have to write your own sorting algorithm or your own hash table, like how to do certain types of things. They're all kind of done for you. If you want to open a socket, you just say, I want to open a socket. So instead of having to have your own arsenal of things that you bring into your program or rewrite how sockets operate every time, you just kind of speak at a more higher level, I want the computer to do this. Instead of, I want this action to happen.
And this is based a lot on application frameworks, like Brian was saying, like this collection of classes. So when you actually run software, it runs on top of another layer where all this stuff is defined. You also see from this the Java realm and that sort of thing, where your code is actually running in like a virtual environment. So you have like a program that the code runs through, and that's what it executes on. Some examples of these generation is Visual Basic, C#, Java, and Ruby.
Another way to categorize the types of language is to separate them between procedural language and object-oriented language. So procedural language you can basically see as a kind of like a ticker tape that goes into a machine, and the machine just sort of runs down the line of tape. So the next instruction, next instruction, next instruction. Whereas object-oriented languages is more of like a bunch of balls in a tank, and the balls do different things.
So these procedural languages, some examples of that, we have Fortran, COBOL, C, and BASIC. They pretty much are designed mostly of variables, functions, and primitive data types, which we haven't talked about. Primitive data types, it's a very simple concept. It's just
like a letter or a number.
Right, basically that's anything that can be expressed as a number that can retain a value. A character is a number, which we talk about later when we talk about ASCII. Of course, a number themselves, different types of numbers like floating point numbers.
A Boolean value. If
Boolean
it's true
value.
Or false. So object-oriented languages also include all of those, but they also include a collection of these into larger objects. So you can create a new object that contains a unique set of variables, functions, and data types, which define new data types. And you can start to build your own language.
And if you don't understand that, don't freak out at this point, please, because Brian and I will go very in-depth in the object-oriented concept later.
We just want to just expose you to the idea.
Brian and I also compiled a list of methods of execution, and we believe that this is important because depending on the type of software that you're using and developing, you need to know the type of environment that you're working in. The most primitive, but also the most efficient method of execution is a compiled execution, which is when you write a piece of software and you take the code file, and then we use a piece of software called a compiler, which actually converts that code file into machine language.
So you could see a compiled program as every word that you type in a program is basically a shortcut for a larger block of machine code. So if you use a word that is a part of the language, it's just a long series of ones and zeros that get processed by the computer.
Yep.
So before it runs, it actually converts it. You know, it uses all of those shortcuts and builds out the file and then runs that.
And when you have a compiled file, you execute it as a compiled file, which is a little different than this next item, which is an interpreted file. An interpreted file technically runs as compiled, but it doesn't pre-compile it. The program is actually read by a program that's called an interpreter that runs through the code, and as it's executing it, starts compiling it, and then runs that compiled code.
Right. So if you get a compiled program, let's say you're in Windows, and you get an executable file, which is a compiled program, you can't open that program in a text editor.
Oh, you can,
but
you're not going to have any idea what's happening.
It'll just be gibberish. Whereas an interpreted program, if you get that file, you can open it in the text editor, and you'll actually see the programming language in the file.
Exactly, right.
And you'll actually run that through an interpreter. So you can, up until the point when you run the program, you could change that interpreted script.
Right.
After this is the framework and virtual machine execution types, where you have source code that's converted to common runtime language, which is the same across multiple platforms, and gets processed in a virtual machine and then compiled. So that's kind of complicated, but when you compile something, you compile it for a particular operating system. So you compile it for Windows, for a 32-bit processor, for a 64-bit, whatever.
Exactly.
When you run in a virtual machine, you install a virtual machine that's designed for Windows 32-bit or a 64-bit processor on another operating system, OS2 Warp, whatever. And the common runtime language, which came from your source code, can execute on any of those virtual machine installations.
Absolutely. And that's one of the, you'll see most languages have moved in this direction in modern times for, to solve the cross-platform incompatibility problems that we've had over the years. So you can write something in Mac OS and take that same code and run it in Windows or Linux or Unix or whatnot, and without having to recompile the code.
And Java is the most popular example of this. Lastly, there's emulated, which means that you can run a program on your operating system that simulates another operating system, and within it executes a program for that operating system. So, for example, you can, in Linux, run a Windows emulator that executes a program compiled for Windows in Linux.
And the beauty of that is that, what Brian is saying is all true. Now, we were just talking about frameworks of virtual machines. Well, there are situations where you have a program that is compiled for a single platform that is not written in a language that runs on top of a virtual machine. Like, one example of this is, in the example Brian was talking about was in Linux, there is an emulator called Wine. And Wine will run Windows applications. So you could take Wine and install Adobe Photoshop in Linux, and you could run it in your Linux operating system.
Other common times you see emulation is on console emulators. So some people will play like Super Nintendo on their phone, and things like that. So,
and you'll also see in terminal emulation. Now, technically, this isn't a matter of execution, but if you work in a situation where you're working on mainframes, you may encounter this.
So I hope this has been a helpful overview of the kind of the core concepts of languages. And thanks for watching.
Yep, we'll see you in the next one. Hello and welcome to the Wibbit.net video tutorial on common modern languages.
And the people who love them.
Yes, the people who love them. What we want to get across in this video is we just want to kind of go over some of the major languages that exist today that you would most likely encounter in a career in software development.
That way you have basic exposure of what's most often out there. Mm-hmm. So as you go from company to company or go to look for jobs, you can kind of have a heads up of what you're likely to run into.
We also kind of try to mention how languages are used. So if you're given a certain type of project, you have to make the selection on, well, which language is actually best to do this.
Absolutely.
So the first language that we want to talk about is Brian and ours favorite language of all time, I would say, right?
Yeah, I agree.
It's up there. All right. Is the C programming language. This is commonly used in anything that requires fast execution. So things like system software, drivers, operating system code, graphics processing, gaming engines, multimedia encoding, like the MP3 encode, decode, all that kind of stuff is written in C. And pretty much any operating system that you encounter, if not entirely written, is mostly written in the C language.
So the C language is not necessarily the highest level language or the newest generation language. It's been around for quite some time. It's also arguably not necessarily the easiest to use or fastest to use, but it is very quick.
Absolutely.
The execution time is very fast.
The machine code that it produces is very efficient.
Yeah.
And you get to dabble, even though it is considered a high-level language, there are many elements of C that allow you to dabble in actual memory allocation, memory usage. Like if you want to get deep, you can get so deep that your program, that you have complete control over every aspect of your program's execution. Some famous programs that are running C code that we found, or a C derivative, are Microsoft Windows, Mac OS, the Linux kernel, one of Brian's favorite applications, Adobe Photoshop.
Or at least a lot of components of the heavier graphics processing parts of.
Right. And MySQL. I mean, of course, these aren't all written in C, but some of the libraries that these use are written in the C language. For the most part, something written in C is not something that you'll usually see. A lot of it is things that are happening in the background.
Right.
Like you won't see too many graphics things written in C.
Right, user interfaces, yeah.
Right.
So C is an older language, but it is very alive and it's very well.
Oh,
and
yeah.
It's very common to be used still today.
And C's best friend, C++, is the next language.
So this is better for higher level applications. C++ has conveniences, some libraries that are nice to use. So some things like built-in support for strings. So C++, which is a descendant of C, has a lot of similarities to C in the structure and how the language looks and how you interact with it. But there are some improvements, some people would argue.
And its relationship to C is so close that, for the most part, you can take anything written in C and you can take a C++ compiler and you can compile it.
That's true. Generally speaking, this language is used for network software, network drivers, comm software, service layers, some more of the back-end stuff, some more of the lower-end programs, but not quite at the system level, not quite at that base level.
But you can dabble in that level.
Absolutely.
That there also is a derivative of C++ called Visual C++, which some people may be familiar with.
Yep.
And that is sort of the Microsoft interpretation of C++, where they kind of redid C++ and added other components like graphics libraries and that sort of thing.
Microsoft Fried Chicken.
Microsoft Fried Chicken, the MFC framework, exactly. So there are subtle differences. If you are writing something in Visual C++, not everything written in pure standard C++ will compile in Visual C++. So there is actually a difference.
But it's Microsoft, so it shouldn't really be any surprise.
Yeah.
Some famous programs that were written in C++ are some of Google's backend, some of Amazon.com's backend software, Firefox, Chrome, Maya, which is a 3D animation and rendering software, or KDE, a Linux shell.
C had a baby called C++, and then the C++ baby is C#, I guess.
That's right.
C# is a fantastic language. It's implemented in many applications today, ranging from desktop, web, phone applications, mobile devices. It is a pure object-oriented language that offers you all of the modern features that exist today. From this, we also get a lot of great conveniences like automatic memory management, which some of you guys that have written in C and other lower level languages know that manually managing memory can be quite a pain. C# removes this responsibility from the software developer.
And one of the reasons C# became popular is as computers became faster, paying attention to memory management at that low of a level wasn't so necessary. Because the computers were so fast, you could be a horrible programmer and write very poorly managed memory. The computer will still function perfectly fast for your purposes. So there's a lot of applications, fortunately or unfortunately, that are written that aren't very efficient. They're not necessarily written that well, and they don't need the consideration that some need. So C# can be a good language for those too, where you need faster development turnaround time and are not as concerned with system performance. Also, the most common tool to write C# programs in is Visual Studio, and Visual Studio has a lot of features like IntelliSense that bank on the advantages and disadvantages of the language. Visual Studio, which is the .NET implementation of C#, is not the only place you'll see C#. You also see it in Linux with the Mono library.
Very commonly used in ASP.NET, web programs, web services, and also, as we were talking about, embedded Windows, which is really interesting stuff. Now, even though I said just a moment ago that C# is a descendant of C, you could make an argument that C# is a descendant or a competitor of Java.
That's
Maybe
true.
not a descendant of Java, but a competitor because it came after Java. And those of you that are familiar with Java know that the C# language and Java share very, very strong similarities to how they work.
Absolutely. Perl is a scripting language, and arguably the most popular scripting language. It's object-oriented, it runs in an interpreter, and it's very common with back-end administrative type of scripting. Things like file processing, system administration. You'll see it in CGI scripts.
For web stuff?
Yeah. Web scripting. Sometimes with network programming. A lot of quick and dirty programs.
Oh, yeah.
So if you need something to just kind of move through each file in a directory and do something to it, a Perl script is the kind of a fast use.
You'll be hard-pressed to find a language that offers you a much quicker way to do something like that than Perl.
So generally speaking, if you see a program written in C, in C++, in C#, and Pascal, and Perl, and a lot of other languages, even in Java, they will basically look the same. The basic layout of the code, how blocks of code look, and how program language flows when you look at it, will generally look all the same. They've all kind of been rooted in the C language. And so this makes Perl more accessible to developers that come from that lineage of understanding.
And since Perl works so well with cross-platform compatibility, anybody that gets involved in server maintenance where you see like cron scripts and that sort of thing, a lot of times you'll see stuff like that in Perl.
Absolutely.
The next language that we're going to talk about is technically not a language, but it's extremely important to understand. Language is part of the acronym, but it's really not a programming language as much as it is a formatting language. It's used by many applications. The most common way that we see HTML as programmers is in web. Although I do want to say that it's not only used in web.
Absolutely not.
That's just its most popular
A web
implementation.
browser is the most common application to display it.
Instead of using things like declaring objects and stuff like that, which we haven't really gotten into yet, it uses a tab structure to identify objects. And most objects in HTML are either predefined in the language or an extension, whether it's some sort of ActiveX or COM object that's used on the local PC, like a Flash player, that sort of thing, is an extension. You would see Flash code in HTML, but it's not. It's added to HTML. HTML is also seen in conjunction with CSS, and that helps with dictating formatting. So instead of going through all of your elements, you can just write a basic HTML page, slap on a CSS, and then everything will just kind of fit to that format.
Also, CSS sometimes can normalize some of the differences between browsers.
Good point.
But one of the things to consider with HTML always is that HTML is not equal in all browsers. There is a standard for HTML.
And Microsoft chooses not to follow the standard.
Ever.
But every other browser, like Opera, Firefox, Chrome, pretty much work fine. But you'll find stuff that's written specifically for IE. You'll even see some JavaScript code where there's a condition that says, if you're running an IE, run this code.
You'll see that a lot.
Right, if you're running Firefox, run this code.
You see it all the time.
Oh, yeah. One thing to kind of attach to HTML is XML. It's a similar structure to HTML, but it doesn't really process or read like HTML. It basically is a standard for containing and storing objects in a tagged formatted language similar to HTML. So they are related in their syntax, but they're not really related as a language.
Right. Next is JavaScript. JavaScript is not always, but most often found to be embedded in HTML pages. So JavaScript will execute in a browser and perform logical operations and executions within a website. And this is client-side scripting. This is downloaded with the HTML code, and it will execute on your computer on the client side. And this helps to create dynamic and interactive web content. Within JavaScript, HTML elements can be declared as objects and manipulated like a C++ object is. So you have access to the HTML elements from the scripting language. And it's called JavaScript, but it has absolutely nothing to do with the language Java.
I've never really gotten a straight answer from anybody about that.
I think it was trying to coattail it. It was trying to capitalize on the growing popularity
at the time,
of
Java was exploding.
Generally speaking, you'll see this in the web and on mobile development.
Yeah, like something simple like when you go to a website and you put your cursor over a button and it lights up, 9 times out of 10, that's the JavaScript that says that you take the object that is the image, and you say when the cursor is on top of the object, swap it out with this image.
Right.
What do we have next?
PHP.
PHP. Now, there is an urban legend. I don't know if this is true, but I've heard this from many people that when the people that created PHP released the language, they didn't have a name for the acronym. They just called it PHP. When the language became popular, they had to think of, well, what does PHP stand for? I don't know. So let's call it PHP Hypertext Preprocessor. So if one of the creators of PHP is listening and I'm wrong, please send me an email, because for many years that's what I've been known to believe that's what the name came from. We were just talking about client-side scripting languages. Well, PHP is a server-side scripting language. It creates dynamic HTML and JavaScript content on the web server.
So you could basically see it as when you request a web page, HTML is sent back.
Yep.
And in PHP's case, a website is requested with arguments, and based on those arguments, a certain result of HTML is returned.
Like something simple. Like you can set user sessions or session variables, which is basically when you go to a website, you can have a variable that's designated to just you. So you can have things like login scripts. So if you're logged in and you've been authenticated, you can then view this script. So that's how when you go to like a social networking website like Facebook, which I think is written in PHP, when you log into your Facebook account, they can recognize who you are based on these variables that you have stored locally. One of the reasons why PHP kind of exploded, it's extremely easy integration with MySQL or MySQL has pretty much made it. PHP is here to stay.
And the fact that PHP and MySQL are both open source and don't cost any money didn't hurt it either.
Oh, absolutely. And that's why we also mentioned here as part of the poor man's arsenal.
Absolutely.
So, Brian, explain to us what the poor man's arsenal is.
It's common to have a combination of an Apache instance, which is a web server, which will serve your HTML, running on Linux operating system. Apache is open source, doesn't cost anything either. MySQL, which is the database, which is in the GNU license, and PHP. You now have a web server, a database, and a way to create dynamic content. And the dynamic content usually comes from things that are stored in a database. At almost no cost, or at least at only the hardware cost, you can be up and running with a fully functional dynamic website.
And a close resemblance to the Perl syntax didn't hurt it either.
That's true.
You know, I mean, you can look at PHP code and you could easily mistake it for Perl if you didn't know some subtle things about it.
And a lot of people actually be mistaken in thinking that PHP stands for the Perl Hypertext Preprocessor.
That's true. That's true. And you know, guys, if I am right and you guys couldn't think of a name, that would have been a very good one for you. Ah, here we are. Is it my turn or your turn?
Either way.
All right. Here we go, guys. This is the glamorous Objective-C programming language. Now, I wanted to make sure that we put a pronunciation on here because there is some discussion on the pronunciation of this language. People don't want to say it's Objective-C because what are you objecting to?
Right.
It is Objective-C because when it was originally developed, it was coded, I believe, object-oriented programming in C. So it's Objective-C. It's very commonly seen in Apple frameworks and Mac OS X programming. You also see it heavily on the Apple mobile devices, such as the iPhone devices, the iPad.
And really strongly came out of Steve Jobs and his rogue ninja team of Next Step developers.
Oh yeah, like when Steve Jobs left Apple back, what was it, the 80s, whatever,
yeah.
And he created the next company. He created a set of libraries of the foundation for the Objective-C and Coca language.
So a lot of times when you're using Objective-C, you see things like NSString, NSObject, which is the Next Step object.
Right, they just didn't change the name later on.
Yeah.
Because I think that Apple bought Next, and then Steve Jobs then pushed the Objective-C language into the Apple development, and that's kind of where that marriage happened.
With those developers, yeah. So this is the foundation for Cocoa and Cocoa Touch, which is the GUI components of the Cocoa is Mac OS and Cocoa Touch is iOS. You know, where you're literally touching the screen to interact. The language exploded really in early 2010. It's now 2015, and the language is still around. But as Apple mobile devices became widespread, they were very popular and became very widely used.
So one of the things that Brian and I wanted to mention was that we believe in our hearts that Objective-C was never designed to be as popular as it became. And when you guys start programming in that language, you'll see, number one, from the Apple community and their reaction to simple basic questions. Like, for example, you're writing something in a program. Any graphical program. Let's say you want to know what the text on a button says. So when you click the button, your program will say, you click the button where the text says this. Well, in languages like C#.NET, Visual Basic, and that sort of thing, I mean, you couldn't possibly have an easier mechanism to do that. Now, in Objective-C, in Coca, it's not hard, but it's not intuitive. And when you go to, and Brian and I, this is actually a real life example that I'm talking about here. When you go to some of these Apple discussion boards, you'll see someone ask that question, and the response will literally be, Brian?
I can't imagine a circumstance where you would need to know this or do this. So you have the Starbucks arrogance mixed in with the difficulty of how the framework was inconsistently laid out, and all mixed up in a nice, pompous response like that.
Although Objective-C 2.0 has made some great strides towards this, you can pretty much bank on memory management being manual and
Absolutely.
completely controlled by the developer.
And a lot of reason for this is, namely on the mobile devices, where you have to be extremely cognizant of how you're utilizing memory.
Right, because they're so limited in resources.
Yeah,
right.
Next is Java. We've kind of hinted to the evil brother of C#, which is Java.
Evil brother. Or is C#? Because here's
Actually,
the thing.
C# might be, yeah.
Because we put on this first line, it's similar to C#, or C# is similar to Java, because when you look at the timeline, Java came out before C#.
Absolutely, that's true. Either way, they're just as popular. Really, it's kind of one or the other. It doesn't make much of a difference. Some developers complain about its execution time being slow, and there's issues with cross-platform promises. So Java is supposed to be something that's very usable, something that's very functional, and something that will execute on any platform. In reality, it doesn't really work out that way.
It's absolutely a lie. And that has been one of the big, deep, dark secret lies of Java for a decade.
And it's one of the things that's killing Java now.
Because now there's actually real languages that work cross-platform.
Yeah.
So
one of the other complaints that some people have with Java is that it's forced exception handling.
Mm-hmm.
So it's a bit motherly in how it wants you to gear your program. Obviously, exception handling is always a good idea, and the way that they force you to implement it is smart, but the fact that it's forced bothers some developers from a stylistic standpoint. But it is a very powerful language, and it's very widely used. It's very widely used in government. You see it in desktop applications, web applications, mobile applications. Usually when your browser crashes.
It's because of a Java problem.
Probably a Java applet running in the browser. It's very popular in BlackBerry and Android development. BlackBerry applications and Android applications are both written in Java. Mm-hmm. Mobile Java framework. But despite some of its shortcomings, it's still preferred by many developers today. It's still very commonly used. You do need to know the language. No matter where you go,
absolutely.
You're probably going to run into Java.
A lot of developers live and die by Java.
And it's not going to go away anytime soon.
There are some people that are so in love with Java that they won't accept anything else. And whether that's a good or bad thing, but that's just how it is.
One of the things that is an advantage of Java is if you are a company that needs developers, with Java you can't really have an atrocious developer.
Right. Yeah, that's a good point.
So one of the things I think we had talked about some time ago is that with C or C++, if you have a developer that is not very good, you can have a very, very bad and very destructive program.
Oh, yeah.
But in languages like C# and Java, because there's so much hand-holding and because the frameworks do so much for you, you really can't hurt anything. You really can't spread damage. There's no collateral damage outside of your program.
Yeah, that's true.
So you might not be able to excel as a developer in Java the way that you could in C, C++, for example, but you also can't tank like you can in C, C++. Mm-hmm. So for risk mitigation purposes, a lot of companies, and generally the government for this reason, uses Java in a lot of their applications.
Another reason why Java is also popular, like if you were to go through job listings, you'll see most job listings say, we want you to know Java. In the late 90s, in early 2000s, there was a big push to write in Java.
Yeah.
So a lot of code that exists that runs in production environments has Java components. Mm-hmm. That they may not be using Java as a primary language now, but when you have to support something or fix something, you have to understand the Java language.
Yeah, you have to know the language. Another thing is that while this massive push was happening for Java and while the hype cycle was kind of at its greatest, the school systems also got on board because they saw it as a less expensive alternative to having to teach with some of the costly compilers that they were running and IDEs that they were running. So a lot of schools systems retooled and began teaching Java as the end-all be-all languages to students, which is really a bad choice.
Kind of a shame. Yeah.
It's not a good foundational language to learn.
Yep. You should never learn on Java.
Yeah.
You're absolutely right.
So you don't really start learning to cook a pie without learning how to make dough. I mean, it's crazy. So, but it is what it is. Java will be around for quite a long time. So switching from languages like Java, C#, and C, C++, we'll kind of go into something a little different that's used more for database querying, and this is SQL, a structured query language. And it's pronounced generally SQL. Some people pronounce it SQL.
Some people will say the whole acronym,
Yeah.
but generally SQL. I had a friend of mine that was in a job interview, and he was a SQL expert. Like, he was great at SQL. And when he went to the job interview, they asked him, "How well do you know SQL?" And he said, "I've never heard of SQL before." Well, that's because his whole life he called it SQL.
Oh,
He never knew it was pronounced sequel. So make sure that you note that in case you go to a job interview
Absolutely.
and you don't know that.
So this is primarily a language that allows you to extract and manipulate and insert data in a database. And the language varies between types of database and database servers, but it generally maintains commonalities, common thread. A lot of the flavors of SQL is Microsoft SQL Server, which uses T-SQL, MySQL, Oracle, PostgreSQL, Sybase, DB2, which is IBM's. They all have the similar structure in that they generally say select this from this, where that is that. But some of the functions that you use, like the length of a string, for example,
and
will be different. Syntax
as well. Like in Microsoft SQL Server, it uses kind of like the VB style strings where you don't have to escape.
Yep.
So like if you wanted to put something like a tab character, you have to put it in specially, because if you put, and this may be advanced for some people, but the \T sequence, which everything else in the world uses except for Microsoft SQL Server, it will actually take that as a literal string.
So some people will argue that you can write anything that you could in a normal programming language in SQL.
Don't listen to them.
Don't listen to them, because they're probably insane.
They have lost their mind. They've gotten too deep.
Yes.
And I guess those are the people that just get too comfortable with it.
They're like the Apocalypse Now people. Like, they've been in the war for too long, and there's no returning. You can never go back home.
Oh, God, that's a great analogy. I love it.
But SQL's great. It's absolutely great.
It's fantastic.
You have to know it. You're any application, any website, anything that you do now, you're going to be using data in a database.
Absolutely. And the push in application development now is in that direction, where everything is retrieving data from something.
Absolutely.
So if you don't know SQL, you're screwed.
Yeah.
At least the basic elements of SQL.
And not all places will have a database administrator or a database expert to help you. So a lot of times you go into a development shop and there really is no SQL expert. So it's good to know this inside and out.
And just because they're SQL experts doesn't necessarily mean they know exactly what they're doing.
No, absolutely.
Especially the ones that think that they can write full applications in SQL.
Never trust them.
Absolutely not. The next one that we want to talk about is, I think, a really great language. It's called TCL. Now, TCL is not as common as some of the other languages that we talked about, but if you work in certain industries, you have a 100% chance of running across TCL.
Absolutely. And the industries that employ this language are massive industries. It's
huge.
Finance, healthcare, robotics industries, and they're very widespread. A lot of development jobs, a significant percentage of development jobs are in these industries.
So, I mean, TCL is a scripting language. You can kind of think of it like Perl, for those of you that need something to compare it to. It's interpreted. It's typically found as an embedded language. Now, what that means is a lot of stuff that you see written in TCL is not an application from the start. It's an application that has some need of some customization, and a TCL program is used to customize something within that application.
Right. TCL is very fast, and it's very ideal for short scripts that need to execute many, many times over. So if there's an application, let's say a financial application, and every time you have a transaction of money, and you need to do validation on that amount, you need to perform a short script that's unique to that particular transaction type from a particular source to a particular destination. TCL would be a great fit for writing a short script to evaluate that cost. Or in the healthcare field, if you have any piece of information of a patient gets transmitted across all systems in a hospital system, And those also have to be validated, or they have to be checked to make sure, whatever.
And
transformed to be compatible with other systems.
You will have to consistently take one transaction type from one system, do a bunch of conversions, and send it to another. And this is going to happen thousands, tens of thousands, hundreds of thousands, millions of times in a day. So this is a perfect language for that. And I also want to add one other thing, and I think Brian and I both have a problem with this. Some people actually call this language tickle.
Oh, I forgot about that.
Yeah, and when you read any documentation, you'll actually see like that's a real thing. People call it tickle. And we have a serious, because when you say HTML, do you say HTML? Well, PHP, do you say
Tickle just sounds stupid.
It does sound stupid.
Don't be an ass.
Yeah, just call it.
Don't say tickle. It's TCL.
Call it TCL.
Whatever.
Come on, people. We live in a society here, you know?
Yeah. Have a cup of TCL.
Exactly. Oh, baby! Is this happening now?
Yeah.
Oh. So, and last, drum roll please, but least. Now, okay, some of you guys are going to get angry at this, but the language that we're mentioning last for a reason is Visual Basic. And we have our reasons. So don't hate us now. Listen to us first.
So Visual Basic is visual, beginners, all-purpose, symbolic, instruction, code.
Now stop for a second. Let's analyze what that acronym stands for. Beginners, all-purpose, symbolic instruction code implies that this language was developed and designed to be used by people that weren't computer programmers. As a matter of fact, the actual people that created the basic language have even said that this is for non-computer science people. It was designed to be a stripped-down, dummy language for people to write software that have no business writing software.
Right. Or as a learning tool. Sometimes.
Yeah, like the old Commodore 64s. You know, when computers were first coming into people's houses, there weren't full-blown applications like we know today. You would actually have to get a computer and program it to do something, and BASIC was a common language at that time because you were getting people that did not go through college and engineering schools writing their own software.
Absolutely. But it's primarily geared for non-computer science people. So somehow it's still popular today.
Before you go that far, let's also mention that Visual Basic is a Microsoft implementation of the BASIC language. It is kind of like, the .NET C#. It's Microsoft's flavor of the BASIC language. And in the earlier stages of Microsoft, BASIC was their child. It was their baby. They wanted everything written in BASIC. So in the early 90s, Visual Basic kind of gained popularity and has kind of been on a downward slope. So Brian and I don't really understand why it still exists at all. But thankfully, it seems to be in a decline.
Now, and I'll say this in our defense. Visual Basic is kind of like John Bon Jovi. So you don't necessarily hate Bon Jovi, but you really hate his fans. So we kind of hate Visual Basic for that reason, because a lot of people who write adamantly in Visual Basic are really kind of set on Visual Basic should be the only language on Earth.
Nothing else compares.
No, and they're very, very sensitive about this, and they're very defensive. And I think it's because when they learned this language, Visual Basic is not in the lineage of the C structured languages.
Yes.
So the way that it looks is not like Pascal and C and C++. It
doesn't look like anything. Yeah, right. It's its own thing.
It's very different.
Right.
So if you primarily learned on Visual Basic, that learning curve to jump from Visual Basic to one of the C lineage languages is a lot steeper.
Especially if you've been in it for years, it's almost impossible.
Yes. So Visual Basic people tend to have a very insulated exposure. And I think that maybe, from a more sinister, cynical point of view, probably why Microsoft was such a big proponent of it.
Visual Basic also does have a scripting component called VBScript. And unlike JavaScript, it actually looks very similar to Visual Basic.
Yeah. And VBA, which is Visual Basic for applications. It's kind of like VBScript, but it runs in like Excel and Access, Word even. And
we're sitting here kind of joking about this, but Visual Basic you do commonly see in realms of ASP development, applications for desktop. But one of the trends that Brian and I have seen in the last, 2 or so years is that there are some places that want you to know Visual Basic for the explicit reason of taking code that was written in Visual Basic and rewrite it in another language. That is a very common trend.
Very, very common.
Yeah.
And a lot of times it's most commonly moved to C# and .NET.
Yeah.
Generally speaking.
Even though we went over a bunch of stuff, we have a few things that we left out, not intentionally. These things are still very important, but these are things that you will see, maybe not as frequently, but you should understand.
So if you really want to get into this and be overly vigilant about studying this stuff, a lot of these phrases that we say in here, you don't necessarily have to know, but these are good things to look up. You know,
Right.
if you really kind of want a well-versed domain of what's out there.
Like, for example, if you start taking your web development seriously, you better know Ajax.
Yep,
Like you have,
absolutely.
you know, unless you're doing rinky-dink HTML pages where somebody signs up and they get emails or something, you know, Ajax is a way of basically getting real live content on a website. It transmits a website from a client-server relationship to behave more like an application on your computer.
One of the most popular examples, one of the most popular original examples of Ajax was Google Maps.
Mm-hmm.
So as you drag the map around, you're getting the new content as a result of your action without the page having to refresh or repost.
Right.
So that was an earlier form of Ajax. But now Ajax is everywhere. You would probably not be often to find a web page without it.
Absolutely. You know, you're right. And any legitimate website implements Ajax. Yeah. And there is a protocol called SOAP, a Simple Object Access Protocol. This is not a programming language at all. It's an XML implementation of a message structure that is commonly used in things like Ajax, but also in web services.
So the content that gets passed back and forth between the browser and the server, or the content that gets retrieved from a web service, is usually in a SOAP format.
So envelope is what they call it. So it's important that you don't have to know. I mean, it's rare that someone's going to say, write a program that makes a SOAP envelope, because most web service type software will create the envelope and do all that.
And a lot of frameworks will make this implementation very easy.
But if you're in a situation where you come across a piece of software that's crashing or failing, and it's a web service, take a look at the SOAP request that you're getting. Maybe there's some malformed data.
And if nothing else, the concept is crucially important to understand.
Yeah.
Next is the Unix shell, which is command line interpreter executing shell commands. These a Unix shell script is basically just the commands that you type into a Unix terminal, all written out in a text file and just executed one after the next.
It doesn't have to be a text file, but it can be a text file. You can actually just run it from the command line as well.
Absolutely.
Those of you Windows folks will probably be familiar with batch scripting.
Yeah.
It's sort of similar to that.
A human is probably the most common Unix shell script. Then there's Python. Python is sometimes similarly used in the way Perl is. Python's often used for quick development of math applications. So if you're doing, some strange math algorithm, but you're not necessarily a developer, Python is commonly used. It's a multi-purpose scripting language. It does have a very clean-looking syntax. Some of the IDEs are very nice. Mm-hmm. It's good.
Ruby is a language that you usually don't see, but...
And you usually hear it called Ruby on Rails.
Ruby on Rails, yeah. It's a language that I believe it originated from Japan, if I'm not mistaken. It was inspired by Perl, Smalltalk, and Lisp. The design philosophy of this, and again, this is up to the developer's interpretation, but the design was to be more of a human language and less of a computer language. So it does pride itself on simple usage of data structures like objects and that sort of thing.
And it is an extremely elegant language.
Yeah, it is pretty.
Yeah, it is. And lastly is COBOL. COBOL is a earlier generation, older language.
It's from the 50s, I think.
Yeah. And it's still extremely common. It's common in mainframe software. A lot of high-risk industries will use software that's been versioned since the 60s and 70s. Mm-hmm. And the core infrastructure is still the same, because they can't take the risk of switching to a newer platform that could introduce bugs that are mission critical.
So, some risk-averse industries like healthcare, finance, that sort of thing, you do see mainframe software still in widespread use. And even though this stuff comes from the 60s and 70s, it is still very common.
Yeah, and it's very fast.
Now, you may not be developing in COBOL, but you may run into a situation where you come across COBOL code, and it's good to at least recognize what it is. Mm-hmm. These were just a couple things that we just wanted to kind of attach to the end of our programming languages.
So we hope you enjoyed this overview.
I don't. I hope you had a horrible time. No, I'm just kidding.
The stuff we went over in this is not critical for you to memorize all of it, or any of it.
Yeah.
But basically the names of the languages, how to pronounce the languages, some attributes of the language, you should at least start to get exposed to these.
Cool. So thank you very much, and we'll see you guys in the next video.
Mm-hmm. Welcome to Whippet.net. My name's Brian and this is Kevin.
Hello.
This video is our programming core concepts. So one of the things we want to do with these videos is to step you through a proper process of learning development. And this is the beginning of really getting into the concepts of development. So we want to teach you the core components of what it means to develop before we start walking into languages. And once we walk into languages, we'll start building on that knowledge that we have, which is all based on this foundational video, later with higher level languages and just illustrating the differences. So this is, if you're new to programming, this is a great video. If you've been programming for a while, this is also a good video for you to move through to solidify your foundational concepts of development.
The first concept that we're going to talk about is a very fundamental concept, and that is syntax. It's something that can very easily be overlooked.
Mm-hmm. In every language, like English and Spanish and French, you have a different dictionary. Mm-hmm. So you have an English dictionary, a French dictionary, a Spanish dictionary. Each of these dictionaries is kind of like a syntax.
Oh, it is a syntax.
So when you speak Spanish, you have an O at the end of the word to present a masculine form, and you say this before that.
And an A for the feminine form.
Right, and in English you do something else. So there's a lot of rules, and there's a lot of words that mean certain things in a language, and programming languages are no different. This is referred to as the syntax. Once you start getting into development, to switch to another language is basically to familiarize yourself with the new syntax. So a lot of times somebody who speaks French will have a pretty easy transition moving to Italian. Everybody has a tough time switching into English. So once you have the core concepts, the syntax is really what will move you from language to language. So this is effectively a set of rules that combine symbols and formatting to define the legal structure of a computer program.
Now, legal structure is a very important term to understand. Mm-hmm. When coming up with this definition, we wanted to make sure that we said this in a way that fit what syntax is and how syntax applies to programming. A legal structure of a program is basically this program will run only if it's like this.
Right, if it follows these rules.
Right.
If these rules are broken, the program cannot execute properly.
Exactly, because if you're learning a language, let's say you spoke, I don't know, Vietnamese, and then you come to speak Spanish, for example, you can say a sentence in Spanish, not having that not as your native language, and I can, if I'm a native Spanish speaker, I can maybe not hear a word or two that you've muffed, but understand what you meant.
Right.
Computers, you don't have that advantage.
Absolutely.
So it has to be literal. You can say part of a sentence, but the second that you muff it, the computer, I don't know what you're saying.
Right.
I'm done.
And it kirks out.
It'll either crash or it won't even allow you to compile the program at all.
The next core concept is the idea of a variable. So you've probably been exposed to variables in basic algebra. Mm-hmm. So in basic algebra, you say y is equal to x plus 3. So it's the idea that x is a placeholder for some value, and when you assign a value to x, y becomes something else. A variable is used to store a value in memory. So in computers, that storage location, opposed to your memory or on the paper, is in computer's memory, and that is accessible by the program that you write. And the programs follow logic and math operations closely, very similar to how you'd use it in mathematics, you use it in programming languages.
And there's also a couple of small things to know about variables other than the fact of what it basically is, and that is what a scope of a variable. Most languages, variables are only available within the section that it's defined and within the scope in which it is defined. Mm-hmm. So you can kind of look at it as a hierarchy.
This leads us to expressions. So an expression is a way to allow the variables to interact with each other. So you can say x is going to store the result of 1 plus 2, or x equals 1 plus 2. You wouldn't say 1 plus 2 equals x.
You can't. Right.
So the expression is also the rules on how you express, but it's also the way that you express it. You can also have a variable which is stored as the result of whatever another variable is, right, and a number. So y is stored as the result of whatever x is minus 1.
And x is defined, in this example, x is defined above it. So in this example, like we were talking about scope just a moment ago, that equation can't exist unless x is already defined.
Correct. So x has to be stored from 1 plus 2, or else when you go to store y is equal to x minus 1, x won't have a value.
Exactly.
Because you can't assume that a variable is going to start out as being 0, or that it's even a number.
Right, exactly. Because in some languages are very loose on that type of thing.
Right.
So there's also other things like operations, and a very classic operation that you can do with comparison or expressions, I should say, are concatenation. Mm-hmm. And for those of you that don't know, concatenating is simply just taking one one item and just sticking it up against another one.
Right. Most commonly is found in strings, which are words or sentences or just a sequence of characters.
Mm-hmm. So in this example here, we have a variable called st equals hello, period, space. And in this fake language that we're using a plus symbol. How are plus space plus you. So the result of this, st will actually equal an entire sentence. Hello, how are you?
Also, you can have a conditional operation. For example, you're comparing two things, or you're seeing if something's greater than or less than something else. So in this last case, we have a variable, and we're calling it isTrue. IsTrue can either be true or false. Mm-hmm. And in this case, isTrue is the result of is x equal to 2. X is equal to 3. 3 is not 2. So therefore, isTrue is set to false.
Exactly.
So that's the basic overview of expressions.
Now, every language has its own way of declaring variables. This is just kind of a general overview. Variables are declared differently within Visual Basic and C and Perl. They're all declared different. They all also store variables differently, and they're used kind of differently. But as a basic fundamental understanding of variables and expressions, this kind of gives you an overview of that.
At least a starting point.
Yeah. We also want to talk about arrays and lists. Now, this is a really fun topic, especially when we get into C++ and we start getting into the object-oriented concept of things. We can then really fully understand together the difference between the classical array and the modern array list, or they used to be called like linked lists and that sort of thing, dynamic arrays.
So a variable is of a certain type or a certain data type. So variable x can be a number, or variable x can be a letter, or variable x can be some word or
Boolean?
some sentence or some true or false value. So what type that is considered to be a data type. And in a classical array, you have a series or a set of a particular data type. So a set of integers, or a set of floating point numbers, or a set of characters, or an array of characters.
And one of the important things to understand about the classical array is that the size of the array is defined before. So you can't have, if you are reading in a file, you actually have to say, well, the maximum size of the file that I'm going to allow is this. Because that has to be predefined. You can't just have data coming in random succession, and if there's new data, just append to the bottom. That problem was fixed a little bit later on when we get into the more modern implementation of arrays, which is essentially a list of objects that can be the same or multiple types. They don't have to be the same type anymore. Yep. And there is no predefined length. As long as you have memory available in your computer, you can keep adding values. The second you run out of memory, your program will crash, but as long as there's free memory, you can keep appending values.
So these are also considered to be linked lists, array lists, dynamic arrays, those kind of things.
You'll hear it mentioned in those contexts. So what we want to do right now is kind of show you visually what an array looks like. Now, arrays can have multiple dimensions, which we'll get to in a second, but this is a basic example of an array. So we just have a list. Now, on the top bar, there's just numbers from 0 to 4. That's the index value.
Or the positional value.
So in arrays, in any language worth its salt, arrays will be indexed starting at 0 up into a value.
So in this example, the size of the array would be 5.
Right.
So 0, 1, 2, 3, and 4 is 5 elements contained in this array.
So when we store values in this array, they just append to these values. So if I say, array, I want index element or subscript 2, that's going to come back as value 3.
Right.
So
you can see this as a sideways file cabinet, where the top drawer is 0, the next drawer is 1, and so on. So when you open up drawer number 2, you look what's inside, and inside of it is value 3.
Exactly. Now, a list, a linked list, an array list, a dynamic array, they kind of work a little bit different.
Absolutely.
So if you kind of look at this grid, let's pretend like this is memory. And memory is addressed. So in our little example here, if you want to find what's in memory address 2, 3, you would go over 2 and down 3. So just to kind of get us all on the same page. Now, a dynamic array always starts off with a pointer, which we'll get to in a second. But in basic form, a pointer does nothing else but point to a memory space.
Right, a particular location in memory.
Right, so when we create this dynamic array, we have a starting point that stores the location of the first value. So when I create a value, here I have value number 1 in this example. Number 1, which is the value, is called a node. So the pointer points to a node, and every single node contains its own pointer. And the pointer that connects to a node points to the next element in the list.
Absolutely.
And there's also some more advanced lists that are bidirectional, where there's 2 pointers stored. It stores the next and the previous value. So here, I'm looking at 1, 4, which is value 1. The next value that we add is just thrown in memory space 2, 1. So my pointer points at 2, 1. Then my next memory value points here, and my next memory value points here. Finally, the end of my array ends here, and I have a little black circle here to indicate this is the end of the list. And we kind of alluded to this before, but arrays can have multiple dimensions. So Brian, explain, what is a multi-dimensional array?
We're looking at it from math. If you have familiar with math, multi-dimensional array in its most basic form can be seen as a Cartesian product or a multiplication table.
Yeah, there you go.
So if you remember, the array is a sequence of things. It's a series of things. If every element in that series was another array in itself, then you have a multi-dimensional array. So if you go to element number 3, just to find that it's a 5-element list, you have an array. Another form of multi-dimensional arrays, or a 2-dimensional array, would be a Excel spreadsheet.
That's a great example. But they also expand beyond 2 dimensions. 2 dimensions seem to be, in most practical applications that are application-oriented, not graphics-oriented, 2 dimensions are usually the most you'll see.
Right.
But, Brian, you're much better at kind of explaining this. There are also 3, 4, 5, 6, 7, 8, 9, 10, 11, to n whatever dimension arrays. How does that all work?
So a 2-dimensional array, you would look at like a chessboard, where you say, I'm going to move my chess piece A4 to A6.
Or up 1 over 2.
Right,
like
whatever.
That. Yeah.
So a 3-dimensional array is kind of more like a Rubik's Cube. But imagine that the Rubik's Cube is filled with all of the subcubes. And you can refer to any one of those individual cubes that make up the Rubik's Cube. That would be more like a 3-dimensional array. 4-dimensional arrays become very difficult to represent physically, so they're often represented by using another constraint of time. So imagine a Rubik's Cube that the values change over a course of time. That's a 4th-dimensional array. 5th-dimensional array, we'll need to smoke a bunch of weed and sit down for a while. That's the only way I can.
That's the only way we can get that out of you.
6th dimension, peyote. 7th dimension is acid.
Well, just I mean, those are all great examples, but there are technically no limits to the dimensions of arrays as long as you have memory to store it.
Absolutely,
you can use it. I find a practical reason for a 7-dimensional array, and we'll sit down and. I would love to pick your brain, because you are a very smart person. So as Brian said, and this may be overkill at this point, but this is just kind of a basic representation of a 2-dimensional array. This is an addition table, or is it it's multiplication table, where the top line is index 0 through 3, and then the left side is the sub-index 0 through 4. So if you wanted to kind of use this practically and just kind of see how it works, 3 on the upper right-hand corner times 4 on the bottom left-hand corner will equal 12. And that's how this basic...
So if you were to store these values in this table, you could use that 2-dimensional array as an addition table, or as a multiplication table. Instead of using multiplication in your program, you could actually look up a value in this table to get your multiplication. It's probably easier to multiply, but that's the concept.
We kind of alluded to pointers already with the dynamic array concept. We kind of want to make sure that we get this across so that there's no confusion. So, like we said before, pointers are just simply they're pointing at a memory space. So in this example here, we have variable pointer 0 through 3. And you see that pointer 0 is pointing at memory address space 00, which is 64. And 1 and 2 are actually pointing at the same memory space, 10, which is AF, and 3 is pointing at FF. So one important thing to know is when pointer 1 changes the value that is in 10, pointer 2 is affected. And you don't actually have to say, hey, pointer 2, this value's been updated. Pointer 2 is just pointing at that memory space.
So to think of this in physical terms, if you were to go to a library probably in the 80s, I don't know if libraries are still like this, there was the Dewey Decimal System.
Talking about Dewey Decimal System.
Absolutely.
Oh, yeah.
So you go to the Dewey Decimal System and you pull out the cards, and you go to the card that you want and you pull it out, and that is pointing to a book on a shelf somewhere. So you take that card and that tells you where to go get the book. You go to get the book and you take a highlighter and you highlight some text in there. You put the book back. Mm-hmm. Now, somewhere else in that card catalog, somebody accidentally copied the card that you had and put it somewhere else. Mm-hmm. So you leave and you tear up your card or you take it with you. Somebody else takes that other card and goes to that same location of where the book is. Let's say there was 2 authors, so they put the card in 2 different locations, but they pointed to the same book location. Mm-hmm. Now that other person goes to take that book out, and they'll see the highlighting that you put in that book.
Right.
So that's kind of a easy physical representation. Mm-hmm. Next is the idea of input and output. You will see a lot of references to input and output. Input and output is usually found in a console or a terminal. The way you interact with something, the way files are read, sockets are handled. So, for example, if you write text to a screen, you're outputting that text to the screen. When you type on a keyboard, you're inputting your keyboard input into the computer. When you request a web page, you're uploading the request to the web server. So you're inputting your request into the web server, and then that web server will output the result back to your browser.
Yeah, that's why we mentioned sockets fit in both in this
Absolutely.
case. Yeah.
Yeah, and you can reverse. So input and output, although is subjective to the eye of the beholder, it's still generally universal to the idea that the human inputs to the computer outputs to the human, in a general sense.
Or a program outputs to something and then it gets it back.
Correct.
Right. if it's automated. Dependencies on libraries are important to understand because some of you guys that start running on this will go download a piece of Visual Basic or C# source code and compile it, and it's going to say, "Oh, you don't have this library. Sorry." Well, it's because you don't have the necessary dependency in order to have the ability to run that program or compile that program. So generically speaking, it's any piece of code, any either compiled or uncompiled library or framework or executable that is required for a program to either execute or to compile. And a very basic example of this is those of us that are fortunate enough to be able to walk, you had to learn how to stand in order to walk. So the program in your brain that says, I'm going to get up and walk over there, has to import all of the knowledge that you learned as a baby standing in order to do the walking, because you can't walk without knowing how to stand. Mm-hmm. So that is in this example, that is your dependency. And to kind of move this into the programming aspect, so how does this relate to programming? Well, let's say in C++, if you want to write something out to the screen, like we were just talking about output a second ago, that can't possibly happen unless you import the input-output stream dependency or library so that the C++ program knows how to communicate that information to the screen.
Another core concept is the concept of a function or a method. So a function call will be something like, what is the length of a string? What is the power of these 2 values? So a function is a chunk of computer code that executes and returns a value within a larger program, and it's usually for a particular reason. Sometimes these are called procedures, sometimes these are called subroutines, procs or subs, and a function performs the same action is accessible throughout a program. A method is basically a function, but a function that's contained within an object. Mm-hmm. So methods are found in object-oriented programming. So if we haven't really got too much into object-oriented programming, but an object can contain a variable and a function and other things. And the function that's contained within that particular object is referred to as a method.
One thing to note about functions that's important is functions are part of the modularity concept in software development, which is extremely important to know because that's how software is written. You would never, I don't want to say never because I've read some terrible code. If there's a situation where your computer program has to do something multiple times, why would you copy and paste that code and rewrite it over and over again when you could have a 200-line piece of code and you can make it 5 or 10 lines if you just subroutine out the processes?
So let's say you implement your function and you write it 100 times over throughout your program. Mm-hmm. You start testing your program and you realize it doesn't work in all conditions. So now you need to update that type of action. Now I have to update it 100 times and hope that you're consistent.
Yep.
But if you have it in a function, you just update it once in that function. And the next time that you go to write a program, if it's a common enough action, you can just use the functions you've written before.
Oh, yeah.
And just call them.
If you're smart, you'll write it in some sort of a class structure that you can reuse over and over and over again.
Yeah, a series of commonly used functions can be packaged up into a library that can be used later.
Yep.
For convenience.
So decision statements, just like all the other things we're talking about, is an extremely important concept to understand. It is how a computer makes decisions. So it's a programming structure that's used to make logical decisions based on a Boolean expression, and this happens during the runtime flow of a computer program. Typically, you will see in most languages if-then-else statements or case statements, which are kind of a subset of if statements, but different kind of structure. So just to kind of see how this looks in some sort of a pseudocode concept, we have if a condition is true, then do something, whatever that is. Then next we have a if a condition is true, then do something, but let's say if that condition is not true, do something else. That's where the else condition's from. Thus, if then else. There's also another condition where we have an if a condition is true, else if another specific condition is true, and then the fallout is if nothing else is true, do this, which is the else condition.
This is an extremely important concept.
Oh,
This is definitely something that you will use over and over and over. It's like breathing with programming. It's a very important concept of programming. Decision
statements, although in the flow diagram exist in if then else and case, are not confined to that, because we will also run into the concept of loops.
Absolutely.
And loops are based on decisions. So Brian, talk about loops.
So a loop is you have an if, then do something else. In a loop, you have an if, then do something else, but it will constantly reevaluate the condition until the condition is true. So until
the condition is false.
Or until the condition is false.
As long as the condition is true, this code will continuously execute on it.
So it's a way to iterate through a block of code while a condition is not met. Some of these examples, which we'll get into, is a while loop, a do-while loop, a for each. So first, let's take a look at the while loop. A while loop is a particular structure that executes like this. While this condition, do these following things. So in this example, we set x to be 1. While x is less than 10, which it is from the onset, do these things. So while this condition is true, we do the following things. We print x, and now we're going to store x as x plus 1. Once that block of code is finished, we go back to the while. So those two things underneath while will continuously execute until the condition is false. So x is now 2, x is still less than 10, we do it again. Now we print. So now it's going to print the number 2, then print the number 3, then print the number 4, and eventually x will be 9, which is less than 10, and then x will be 10, which is no longer less than 10. Once this happens, we will break out of this block. So once x is stored as 10, we won't print x, we won't store x as the next increment, we'll just continue on with the rest of the code.
Yeah, there's one of the main reasons why understanding expressions and decisions is important is because what Brian just went through was a great example of how this code will work and will break properly. But let's just say by accident you put a minus sign where we have x plus 1. Let's say you accidentally wrote x minus 1. You fall into a condition which is known as an infinite loop. It's a loop that never exits.
That's a very good point.
And it's a very common type of problem that you'll see in software. So a lot of times that's just operator error. You just accidentally put something in wrong. Maybe your code is working fine, but then there's like one small condition that throws it off. So it's your obligation as a software developer to understand this. And also one last thing, which we should have probably mentioned a moment ago with loops, is there's two important things that loops do. They either break or continue. Now, in the condition of a break, is what Brian explained, a loop will break once the test condition is no longer true. Having said that, you can actually manually break a loop by whatever the language specifies as that command, which we'll get into later.
With a break statement.
Exactly. And a continuation is just what Brian was saying is, you don't even think about it. A continuation means this iteration is complete. Now let's go test a condition one more time.
So the next type of loop, which relates to the while loop, is the do while loop. So in our previous example, we said, while this condition is true, we do the following things. This sort of reverses it. It says, do this first, and then we'll evaluate the condition, determine if we should iterate through this again. So in this case, we have x is stored as 1. So now we do this. We print x, and we increment x to now 2. So while x is still less than 10, we do this again, and so on until that condition is false, and then we continue to the rest of the program.
So the important thing to take out of the do-while loop is the do-while loop must execute at least one time.
Yes.
The while loop does not.
Absolutely.
The while loop cannot ever execute if the set value, the set condition is not true.
Mm-hmm.
The do while has to execute once. The next loop that we're going to talk about is functionally one of the more useful loops. It kind of combines a couple of different programming structures into one loop statement. You can technically do anything with a for statement with a while or a do while if you really wanted to do the extra work. A for loop basically is a structure that executes code from a designated start and end point, and this is built into the structure. So if you look at our example here, a very common usage of a for loop is iterating through an array. So don't worry about this syntax. This is just junk just to kind of get the point across. We have an array set to size 3. In element 0, 1, and 2, we set values, value 1, and value 2. So below we have our for loop structure. So we're going to set a value, I. It's typically used in for loops. I stands for iterator. So you'll see that very common in for loops. And I will be set to 0, while I is less than the length of the array. So in this case, it'll be 3. Increment I. So I++ is used in most languages as shorthand for I equals I plus 1. So then we'll just print the value, and then we'll continue until that middle condition, I is less than array.length, is no longer true. And then the for loop will exit. Lastly, we have the for each loop. Now, the for each loop is a structure very similar to the for loop, except for it doesn't take the count into consideration. In most cases, a for each loop, and I think all cases, a for each loop is used in the context of an array, where we have an array just like we had before. We go for each, and then the item is going to be the value of that index in the array, which is called the enumerator.
Yep.
And that value in the array, print the item. So this will just run through and print value 1, value 2 out to the screen without you having to index anything.
Okay, so let's take a step back now and take a look at loops in general. So just to make sure we drill in the point, we'll see that loops are generally used always to iterate through some sort of list or to traverse an array. It's an extremely common structure. You use it all the time, and there's probably not many algorithms that don't use some sort of loop.
That's true.
You're always going to be using loops, so no loops. So if you're lost at this point, or lost at the end of this video, maybe just kind of keep going through it again a few more times, look at some examples. Even Wikipedia is not a bad source for looking at loops.
I mean, to see how common loops are in algorithms and even basic stuff is when you get up and you walk over to get something, the process of you walking is a loop. Because for each step until you get to your destination, you're looping through a process in your brain which is foot forward, or falling forward and catching yourself, which is what the act of walking really is. So let's take a look at a kindergarten example. Let's do, we want to eat cookies. So let's say that we want to eat exactly 5 cookies. So what loop structure would we use to do this?
Let's find out.
Okay. We're going to use the while loop. So what Wibbit the Frog here is going to do is he's going to eat 5 cookies. He's going to eat 1 cookie until he's eaten 5 cookies. So he has 1, 2, 3, 4, 5 cookies. He's met the end condition of this loop. The loop is now complete.
So the while loop works just like it sounds. So we want to eat 5 cookies. We, in the beginning, haven't eaten any.
Right.
So while we haven't eaten as many as we want to, we eat one.
Exactly. Yeah.
So I mean, it's very, very natural language.
So that was a great example, Brian, but there is another loop structure that we can use to eat exactly 5 cookies, and it's a lot less lines.
That's true.
And what is that loop?
It's the for loop.
The for loop.
So this is kind of similar, but in this case, whereas before we defined how many cookies eaten and how many cookies we want to eat before we even entered in the loop, this can all be self-contained in a for statement. So this acts the same way as the last loop, but we can just say for. We start with initially there's no cookies eaten. We want to eat up to less than 5 cookies and increment by 1. We're going to eat 1 cookie at a time. So for every one of these iterations, we eat a cookie, eat a cookie, eat a cookie, until the number of cookies we've eaten is 5, and then we break out of the loop.
Oh, and now he's getting a little full, so we may have to go to the next day. Oh, good, look at this. The next night...
This frog's going to blow up with all these examples.
Yeah, but he's getting a good meal. A good hearty meal. So the next time or the next night...
Do frogs eat cookies? Should have been a jar of flies, maybe.
It should have been a jar of flies.
Anyway.
What the hell? Man, we suck.
But who has a jar of flies sitting around? I mean, that would just be weird.
Well, Alice in Chains had a jar of flies. Remember their album, Jar of Flies?
No, but they would.
They had an album called Jar of Flies.
We're so intelligent, you just don't understand what it means to be a jar of flies, flies, flies.
That does sound like a David Bowie record, though.
Yeah, right.
So the next night...
A jar of flies in space, man.
Space. With a shiny spacesuit. So the next night, Whippet the Frog wants to eat at least 1 cookie until he's full.
So not some predefined full, but just some arbitrary, abstract... Full.
Yeah, whatever my fullness is right now, I'm going to eat at least 1 until I don't want to eat anymore. So the loop structure that we would use, Brian, is the do while.
Right.
Because as we explained before, in a do while structure, the loop iterates at least 1 time until the end condition is met. So in the do while, Whippet the Frog, as happy as he is because he had a whole night to digest the cookies from the night before, he's going to eat 1 cookie and then he's going to check. Do I want to eat more cookies? So he calls the I am full function. So he's going to have another cookie. Then he makes the decision, 2 cookies was enough. So now eat more cookies is not true. So the loop exits.
So now let's look at another example. So even later that night, you want to eat the rest of the cookies in the jar. So you don't really have a lot of the controls that the other loops have. You don't have the conditions of until I'm full or up until 5 cookies. You just want to eat everything in the jar.
You've made the decision. This is it. I'm getting fat.
I'm
tonight.
committed.
Yeah.
Like that cookie jar is mine.
There's nothing you can do about it.
Get in my belly. So we would use the for each loop.
How do you know that? Oh, because the slide says so.
So in this case, and this is in a lot of languages, pretty much most languages have this, and it's a very convenient way to just move through everything in a list. You basically just say, for each cookie in a jar, eat a cookie. So it just grabs the entire set of cookies, and it just goes every single one of them until there's none left.
And then, oh, now he's really full because that was a lot of cookies.
This leads us to another core concept, which is a concept in object-oriented programming called classes. A class is a structure that contains methods or functions and attributes or variables to form the concept of an object. So a class is the definition of an object. When you define the class, you're defining the potential of the object. So it's an encapsulation of the methods and variables. When you use a class, you instantiate a class into an instance. So somebody designs a car, and they design all of the features of the car, but then a car factory produces an actual physical vehicle, which is the entity. So the class is the potential of the entity, and the instance is the entity. So when you go to use an object, the object will be created from a class definition of that object type, and will have that collection of properties, and you can actually store values against that object. So you can say, this car is red, that car is yellow. Those are different attributes, but the definition of the car is the same type of car. So that's an object and then an instance of an object. Next, we will see a visual representation of how this works. So here we have class potential of a person. So now we're going to try to define out a person. A person might have the following attributes. A person might have a first name and a last name attribute. A person object could have a method to get the first name and set the first name, get last name, set last name. So when we call get first name, it will go and look to the attribute first name and present us that value. When we call get last name, similarly, it'll go to the last name attribute and it'll present us that value.
So it works simply like, hey, Brian, what is your first name?
My first name is Brian.
And that is because Brian's get first name method in his brain went to his repository of attributes and pulled that out. Now let's say that Brian wants to change his name to Byron. What do you do then?
Then I set my first name to Byron and realize I just set my name to a typo and feel like an ass. So when we develop a method and we go to write the instructions for set first name, all we really do there is first name is equal to whatever we told it to input, and set last name stores the last name value that we tell it to. We define the person as something that contains these attributes. So now we're binding these two particular attributes to the concept of a person. Also, these methods only apply to this object type person. So now we have the class definition of what a person is. A person is something that has an attribute first name and a last name, whatever those are, and has methods that interact with the attributes.
Now the important thing to realize at this point is even though we have a class that is defined, we don't have a person.
No. We just have the concept of a person.
Exactly. So now, Brian, what do we have next?
We have a person.
Oh!
So we instantiate the person class to be a particular person. So a person has attributes that are defined, like this blue person is blue and has a first name Bob. Blue Bob. Now we can make more people. So we can make more instances of people. One which is green,
which is
Gary.
probably an alien of some kind.
Yeah. And a red person, which is Rosie. So we have Bob, Gary, and Rosie. They're all different instances of people that were created by our definition of what a person was.
Now, one thing also to mention that we didn't mention here, but we will, is there are a few other structures that are closely linked to this concept. That is the concept of a structure union and an enum. Mm-hmm. These are all types that are so close to the object-oriented concept, but they're just not
quite that.
They just haven't taken that leap. So if you understand this, then the concept of the other things are going to be easy, and that's the reason why we didn't mention them in this presentation.
Absolutely. So I hope this was a easy to understand way of approaching the core concepts of programming, including some of the concepts in object-oriented programming. Thanks for watching.
Welcome back to the Wibbit.net Introduction to Programming tutorial. In this video, we're going to talk about flowcharts.
Hooray!
Yay! Now, one thing to keep in mind about flowchart, Brian, is they're very boring.
Yes.
There's nothing fun and exciting about making a flowchart.
Absolutely not.
No, and if you work in a job that requires you to do this with planning, and it's actually a really good idea whether you're required to or not, you're going to hate it, but when you get towards the end of the development life cycle, you're going to really love the fact that you took the time to plan your project.
And if you find yourself not using flowcharts, what you will find yourself doing is thinking in terms of flowcharts. So one of the things that's very important with flowcharts is something that's very intangible. Understanding flowcharts will change the way you think about programming. So it's crucially important to understand so that you can train your mind how to visualize a program. So even though you might not actually take the time to draw it out, you will take the time to think it out. It will become how you think of a program.
So as a basic definition, flowchart is a diagram that has predefined symbols and it represents a algorithm or a process. Now, some of you guys may have been exposed to many different types of flowcharts. Well, number one, not every single flowchart is the same because symbols are not standardized.
No.
And number two, flowcharts exist for other things besides software development. Mm-hmm. So you'll see many things expressed as flowcharts that are not going to be relevant to what we're going to be talking about.
Right.
Because we're going to gear this specifically for software programming.
And if you're not exposed to flowcharts, the most basic idea of a flowchart is traffic signs.
Okay, yeah, I can see that. Yeah.
So when you're driving, you use flowcharts all the time. You stop at a stop sign. You have a traffic light. It makes a decision, decides to turn green, which allows you to go on to the next step, which is the next road, and so on. Flowcharts are used all the time, but the way that we discuss flowcharts is just one view of flowcharts for software engineering. And in using these, you can define out the requirements of how a program will operate, how a program will make decisions, just like how we make decisions in traffic.
The first section of flowchart symbols that we're going to discuss are process operations. What we have on the left is a symbol with the text inside that is what it is. On the right, we're going to have the definition of what it is. Like we said before, these are not standard. The typical rectangle indicates a process or an action. What is that? What is that shape called? The curve?
Rounded cornered rectangle?
Sure.
Rectangle with rounded corners?
That works. That is a representation of a process that is an alternative to what may be considered a regular process.
Right. So a process is like a task or performing a task, an actionable thing to do.
Mm-hmm. The subroutine item or symbol represents an instruction that can be executed multiple times. Like we were talking about before about functions and methods that would be expressed using these types of symbols.
So this is more process operations, including a preparation, manual operation, and delay. Preparation are measures that must be taken before defining a process. A manual operation, which you can see in the next symbol, is a process that cannot be automated. So it's something that requires human intervention.
Like, turn on your PC.
Right. And then this bullet shape is the delay, which depicts a waiting period. A lot of times a delay will either say delay or will represent some time value like 5 seconds.
And a lot of times you'll see preparation. Sometimes people will use this to store parameters arriving. So if I'm writing a flowchart for a function, my preparations are make sure that this function knows this, this, and this before you continue. So the next section we're going to talk about is flow. And some of the basic flow diagrams you see will say arrow. This goes over here. So the first one is just a solid line arrow, which indicates the direction or the flow of the flow chart, whereas the dotted arrow or the dotted line is typically used in comments or when showing an alternative process. Comments will not have the arrow at the end. Typically, a comment is dotted lines followed by a circle or a box that just has human readable text in there to explain a section of the flow chart. The reason why there's no arrow is because a comment is not part of a flow. It's just, hey, did you know this kind of thing. And when you're drawing a flow chart, any situation where you have lines crossing, it is standard to have a little loop
row bump
that shows that this one goes below this one, because otherwise, if you don't have that, what that means is the flow goes up and continues on to this line.
Or splits off into these two lines.
Exactly. So it's important that you have your little road crossing where your lines overlap.
Next is the terminator symbol. This is the beginning or an end of a sequence. Do this, this, and that, and then terminate. The next is a connector. It connects two sections of a flowchart. So if you have a flow that is grouped into logical segments or clusters, you can connect these with connectors.
And typically, when you have a connector, it'll say like one matches with one, or it'll be labeled so that you know what it connects to.
Right. If the connectors go to another page and aren't just in another section of the diagram, then you'll have an off-page connector.
Well, it's like a home plate for like a baseball stadium. Yeah.
So the off-page connector says, see this connector label on the next page.
Yeah, or on page 5 or something like that. So continuing with flow, we have decisions. The flowchart representation of a decision is a diamond shape. And the reason why is you have one line that comes in with multiple ways to come out. Now, in a situation where you have, let's say, more than 3 decisions that can be made, you may have what's called a decision list. Now, a decision list is just a box that has little things on the bottom where the flow would then move from there. So each one of these boxes represents a potential decision to be made. So something comes into my decision, and I have 20 different ways that this can end up, and each one of those 20s goes somewhere else. And that's what the decision list represents. And lastly here, we have the cloud, which typically will represent things like networks, LANs, WANs, the internet, and whatnot. But Brian also mentioned earlier today, I didn't even think about this, but in some flow diagrams, the cloud will also represent something that you don't really need to know.
Right, that's too complicated to describe.
Right.
So just some mess of things that you don't need to understand. It goes into the mess of things, and something else comes out of that mess of things. That's basically what the internet is some
it's just a mess of things.
Indescribable mess of things.
Exactly.
So to wrap up the flow symbols, we have the merge and splitting out symbols. The merge looks like a funnel where you have multiple things coming in and only one thing coming out, or lesser things coming out. The opposite shape, which is if merge is more of a feminine symbol, this is more of a phallic symbol, is the splitting out. So it goes into the smaller end and goes out the wider end.
And that could be used in multiple contexts. I mean,
Right.
you could take the literal usage, like if you were writing a program that says unzip these files, you could use this. But
Right.
there's also like different ways of like taking 5 processes and converging them into one.
Right.
And taking, one process and converging it into many. It's used in many contexts.
Right, or even like in a duplex multiplex way, like Prism.
Mhm.
So you have many rays of light that go to white, many colors that go to white, and then white goes to many colors.
There is also some flows, structures, or symbols that do some form of operation. Like in this case, we have a summation junction. A summation junction simply just takes 2 values, 2 numbers. 2 numbers come in, 1 number comes out. That 1 number that comes out is the sum of the 2 numbers that came in.
Right.
And we also have logical things like an OR. So we have 2 inputs. A logical OR is the output. So 2 things go in, 1 thing comes out.
We also have other things like collation operations, which represents converting data from its input to a standardized form, or normalization operations. We also have the sort operation symbol, which is maybe a little more commonly used. So the sort operation indicates that you have a collection that comes in, and the result of which is a sorted version.
Yep. And you couldn't have said it any simpler than that. So we're going to start talking about some input-output stuff as well. Data is represented by, what is that? What is rhombus? What is that called? I don't even know. I don't know what that symbol's called, but whatever that symbol is called.
Parallelogram?
Whatever. Okay, I'll buy it. That represents data that is either going to or coming from a process. So this is just data that's being stored. You put the values in here. This fun little sideways light bulb that is weird
Or fat
looking.
pencil.
Yeah, okay, or that. That is displaying to the user. Now, typically, the display is monitor, but I've also seen this in the context of other output as well. Even though it's usually used in the monitor context, it can be used in others as well. And this weird-looking other thing, the manual input, sort of looks like a keyboard if the keyboard was broken. This usually indicates input from a keyboard or mouse or any other type of manual input that the user has to provide to the flow of the program.
It also reminds me of the shape of a sign from the 90s. Like, do you
Yeah,
remember the
like-
restaurant from, like, Saved by
Saved
the Bell?
by the Bell, the Max.
Yeah, the Max's.
Yeah.
It has, like, that weird square behind it, because it's
Yeah.
got to be, like, all funky and neon.
Maybe they stole that from flowcharts.
They probably stole directly from Saved by the Bell. I think AC Slater is going to just destroy this flowchart.
Mario Lopez, yeah.
For those of you in India, definitely go to torrents and find...
Well, don't say torrents. That's not legal.
No, torrents of excitement.
Oh, okay.
And investigate time into finding some avenue of acquiring old Saved by the Bell episodes.
Yes. Some more about input-output. These are yours, or these, yeah.
All right.
Sure.
So these symbols represent a document and multi-documents. One of the reasons why these symbols are kind of important is a lot of times a program is the process of solving a real-world problem. And like real-world problems, you deal with documents and files, and those files and documents happen with the computer. So just like you'd say, this person takes this file goes into this process and comes out as this other document, just like in computers, you have documents in a lot of different forms. So document or a file or sometimes an object, it depends on the situation. A document can also be like an image or a video, but nonetheless, it's a document. And when you have a package of documents or multiple documents, you see them stacked on top together like this.
And, you would also see these in the same flow diagram when you have like a one-to-many document relationship where
Absolutely.
you have like a PDF that splits into multiple pages.
Yep,
The input is one document, the output is multiple documents.
absolutely.
Now we're going to talk about some storage. The first one we're going to talk about is internal storage, which in today's world pretty much means RAM. It may have meant something else many years ago, but that's pretty much the story we're sticking to. It indicates stuff that is stored in RAM. The next one is external storage. Now there is some kind of a little bit of fluff here because there are so many different types of external storage. Why would you just want to have one symbol for all external storage? Typically external storage is represented as some sort of a disk shape. A lot of times the fatter the disk, the more that means hard disk. And the thinner the disk, or cylinder, the more that means database.
And sometimes the larger the symbol, the more data it can represent. If you see multiple external storage symbols next to each other, and one's very small and one's very large, sometimes that actually represents some sort of proportion of size and scale. It's also no coincidence that the internal storage symbol looks like a spreadsheet, and the external storage symbol looks like a database.
Yeah.
Or a series of spreadsheets. So,
or a disk, because, like hard disks that aren't solid state are literally disks stacked on top of each other.
So, but these symbols are more abstract forms. And sometimes flowcharts are used for different things. Sometimes flowcharts are just used to represent things very heavily oriented towards network diagrams, or database diagrams, or decision logic diagrams, or computer function diagrams. They are abstract, and you can apply them in a lot of different ways, but conceptually, this is internal and external storage.
And there is a little bit of a slight access or slight momentum change here between external storage and direct access, which typically represents hard disk storage, but that's not always the case. Bryan and I are more used to the external storage diagram, meaning disk space. Right. But the direct access can also represent that as well, which is the same thing, but it's sideways.
Yep. Lastly, we have the sequential access storage medium, like a magnetic tape reel or a tape backup. Usually you'll see these if you have an off-site tape backup process. So do these following actions split off the flow to an SAS symbol, and then have that SAS symbol delivered to the courier that takes it to an off-site backup, for example. Usually that's most commonly where you'll see this. The stored data symbol looks kind of like the direct access symbol, but without the top. And that represents generically a data storage operation, not the location of where data storage is stored, but the process of storing that data.
Now, when we were putting together this presentation, we couldn't think of a better flow diagram than making a peanut butter and jelly sandwich, which is one of our favorite treats. So what we'd like to do here is take this concept and remove it from development and put it into a basic algorithm. And the algorithm is how to make a peanut butter and jelly sandwich. So I guess Bryan and I will just kind of take turns walking through this diagram. I'll start here with our terminator symbol, which designates this is where we begin. The next thing that we need are our pre-qualifiers. I need to know that I have peanut butter, I need jelly, and I need bread in order to make this sandwich. Next, we move into a decision. What type of peanut butter do I want? Do I want creamy peanut butter or do I want chunky peanut butter? Depending on that decision, the outcome will be different. The outcome is different. It's a chunky one or it's a creamy one.
World of a difference.
Yeah.
If somebody gets a chunky peanut butter sandwich that wants a creamy one, that person's going to be pissed.
Exactly. So when you see that when we hit, if we're in the mood for creamy peanut butter, we actually fall into the same logic as the chunky, because the logic from that point on is exactly the same. The only thing that's different is that we have
the action of getting
the jar. So the jar is the variable. So, Bryan, what do we do now?
Let's say we decide we want a chunky peanut butter sandwich, which is the best peanut butter sandwich ever. Chunky
creamy
sandwiches are better.
Chunky sandwiches are for dumb people that have beards like you.
So we get the chunky jar. The jar with the chunky peanut butter.
Or with the creamy jar.
So then we continue on to our next decision. Which is the best type of jelly? Well, indisputably, I don't even know why we have this decision statement on there. It's going to be strawberry jelly.
Oh! High five. Okay, cool. we agree on something.
Our decision could have been grape or strawberry, but it could have also been blackberry or
because
a series of other things.
We only have a certain amount of space to work with. Right. We can have 500 types of jelly on here.
But unlike the previous decision, this could have been a longer sequence of options. So we're going to choose the strawberry option and go down the strawberry path, which tells us the next statement, which is an action symbol, to get the strawberry jar. That then goes, both of those options, regardless of which kind of jars we got, will both go to off-page references, which is the making the sandwich page.
And since that is not on this page, we'll go to the making a sandwich page, which is here.
Hey, look.
So the off-page reference sends us to this connector, which is making the sandwich. Now, when we first jump into this, we need to know that we have 2 pieces of bread. All the other things have been defined. We know what kind of peanut butter we're using. We know that we have bread because that was decided at the beginning of the other, and we also know what kind of jelly we're using. So now let's define 2 pieces of bread. Now I like mine toasted, so my flowchart has toast in it. So I put the bread in the toaster, and then there's a waiting period. Well, I also want to demonstrate some more objects and symbols. So now there's a waiting period because I may run it to the toaster and it's not toasty enough for me. So I will run it again. So that span of time is variable for how long it will take before we move on to the next step, which is a loop condition. Brian, explain.
So once we get into this, you'll see this purple block on the bottom left. And this is our loop condition. So once we've waited for the bread to be toasted, we now do the action of, so this is kind of a do while. So we do this action, spread a tablespoon of peanut butter on 1 slice of toast. Then we go to see if the condition is met. Do we have enough peanut butter? Absolutely not. 1 tablespoon? Are you kidding? So no, we go back and put another tablespoon on. Then we decide, is this enough peanut butter? Absolutely not.
No, keep it coming, baby. I want the whole jar on there.
Yeah. So after we iterate through this about 50 or 60 times, depending on your liking, we decide, is this enough peanut butter? Yeah, I guess so. For now.
We're out of peanut butter.
We can make another sandwich later.
I guess this has to be enough.
So, yes, is the conclusion. So we go to the yes decision line. The yes decision line takes us to our next loop, which is also do while. So this is, we will guaranteed to spread at least 1 teaspoon of jelly on the other slice of toast. Then we ask ourselves, is this enough jelly? No. We spread another one. Is this enough jelly? Yeah, it's enough jelly. We don't need a whole lot of jelly.
And now, this is where it all comes together. We have a process. The process is, now that we've made the decision for the peanut butter that we want, we've made the decision for the jelly that we want, and we have 2 pieces of toast with peanut butter on 1 piece of bread and jelly on the other piece of bread. We then combine the 2 slices of toast where, and this is important because if you do this backwards, you're in trouble, where the jelly side and the peanut butter side connect. Imagine if you did it backwards. That's not a happy sandwich.
It'd be a mess.
So
that would defeat the purpose of the bread.
Exactly.
Because then you just have jelly and peanut butter on your hands. That's just a mess.
That is the greatest idea I think I've ever heard. I'm going to do that as soon as we're done recording this. So once we do that, then we have a complete sandwich. Our process is done. And then we go to the other Terminator statement here, which is an end statement, which is saying the process is complete.
Or if this was a film noir diagram, this would be the fin.
So we've gone over a few things that we didn't really describe, and that is we did have a loop condition. If we go back a slide here, you see that the loop condition we have, and we kind of talked a lot about it, was the peanut butter and the jelly. How much do we want? When we put some on there, these are decisions that you are making when you're making a peanut butter sandwich, whether you're conscious of it or not. You're putting it on there. Do I have enough? That is a loop. So here is a fundamental loop condition. Now this structure fits for both the while and the for, although it's missing a piece for the for structure, and that's the incrementation.
But it's basically in that realm.
Yeah, well, you could technically argue that incrementing could fall into process. But so we have an input from the left. If a condition is true, we do a process, and then we go back, we reevaluate. So you can see here visually a while loop evaluates first, processes second, and the second that the condition is not true, we follow the no flow out somewhere else.
Perfect. Similarly, but in reverse, in a do while, we do the process first. So we perform our process, and then we evaluate whether or not to run the process again. So if the condition is met, then we perform the process again. The process will probably be, unless there's an infinite loop, the process will be changing the variables of the condition. Mm-hmm. So once the process changes the parameters of the condition to not be true, then we'll exit the loop and continue to something else in the flow.
A flow chart that moves away from the peanut butter realm, which is delicious, by the way, and moves more into the mathematical realm, could be a power function.
Yep.
Now, this is a very basic power function, so don't you purists say you can't do square roots and blah, blah, blah. Hey, this is for beginners, okay? So you can see that we have our entry point, our input, and then some other conditions here. So the program starts. The first thing that we're going to do is we have our little crooked Saved by the Bell symbol, which is I want the user to actively put this information in. So our program will say, hey, user, give me X and Y. That's what happens here. So the user is going to say, I want x to equal 3, and I want y to equal 4. So then the next step is data storage. Mm-hmm. Our program has some set values. C, which is just a regular variable, it's going to be short for counter, equals 0. And A, which is short for answer, is going to be set to equal 1. Whereas next we then fall into the loop condition, which Bryan will explain.
So now we get into our loop structure. We evaluate a condition, and if the condition is true, we perform an action. And then we do this over and over until the condition is no longer met. So on the top left, we have our inputs, which is x is our base, y is our exponent, and then we have our counter and our answer. Our counter, which is 1, is less than our exponent y. Our counter is 0 when we start, which is less than our exponent y. So we perform an action, which you see next, which is c is equal to 1. Our counter has been incremented. And now our answer is our previous answer, which is 1, times x, which is 3, which is 3. So we now have c is 1 and a is 3. We reevaluate the condition, and 1 is less than 4. We see that the condition is true again. We perform our action again. Now for the second iteration. So we update this again. C now becomes 2 and A becomes Y. So now we once again reevaluate that our counter number 2 is less than the exponent Y, which is 4. That moves us into our third iteration, which gives us a counter of 3, our third iteration, and an answer so far of 27. Our counter 3 is still less than our exponent, Y, which is 4. So we perform it once again. So this is our fourth and final iteration, which we set C to 4, and the answer so far is 81. And when our counter has been incremented to 4, we evaluate for the last time, which now means that 4 is not less than 4. So we exit that.
So that's no longer true.
Correct. So we exit that iteration, and we continue on to our flow, which tells us to print A, or send the output of A
to a screen,
or whatever the case is,
and then end the program from there.
Right. So that takes us to the final terminator.
So I hope that you guys enjoyed this potentially very dry video on flowcharts. But like we said in the beginning, it's important that you at least have exposure.
Right. So this is like a tetanus shot. You just kind of have to do it.
Yep.
You have to go through this. But we're glad that you did. We're glad you made it to the end, and I'm sure you'll find this useful in later videos.
Oh yeah, and coming up next, leave you on a cliffhanger here. We're going to do something just as boring, but just as important. Pseudocode. Hello, and welcome to the Whibbit.net tutorial on pseudocode. Yeah?
Yep.
You excited about this one?
Yep.
Yes. So before, we had a discussion about flowcharts, and pseudocode is pretty much the next evolution of that. It's sort of taking logic, whether it's a flowchart or your own, you're sitting there just kind of thinking out a program, and putting it into a structure that's sort of like a language, but not really a language, so that the next movement from there is to take that into real code. So it's kind of a gradient transition, where you start with an idea, you move into a flowchart, which puts your idea on paper, you move to pseudocode, which moves it into a computer-type realm, and the next step is actually coding it.
So if you haven't seen the flowchart video, we recommend you watch that now.
Actually, just do it.
Yeah.
Just stop right now and go back and watch it 50 times. So generally speaking, and pseudocode is a very high-level, informal language, and it's not even a language, it's a set of rules that just describes an algorithm. So like the second point here is very important. It is not a programming language. It is also not standard. The way that Bryan and I do our pseudocode is not the same way that company X, Y, and Z do it. It's not the same way that your college may have taught you. It's everyone kind of does it their own way.
The only thing that's common is the basic elements, that there's going to be if statements, there's going to be loops, there's going to be the basic core concepts that we've gone over. You're going to find in there, but how it looks will change from person to person.
We're taking a look at expressions, which we've already sort of talked about, and now we're actually going to start moving into making a real expression. In pseudocode, here's a basic variable expression. On the left side, you have a variable, and on the right side, you have an expression with an equals in the middle. It's no different than any of your basic math equations that you do.
The result of the expression is stored into the variable, just like y equals x plus 1. X plus 1 is the expression, and y is the variable.
So let's take a look at a sample of expressions. Now, what Brian and I have set up here are x and y are going to be set to equal numbers. And then what happens after that, Brian?
So x is set as 5, y is set as 10, and it's just like basic algebra. Now, the variable z, the result of the expression x plus y, which is 5 plus 10, gets stored as z. So now z is equal to 15. Because x equals 5 is above z equals x plus y, that x has already been stored. So it's a top-down, we're running through a top-down approach. So now a is equal to another expression, but this has parentheses. So whenever you see parentheses, you do that operation first, and then you move outside of it. So first we do z plus x, and then we do z plus y, and then we multiply the result of z plus x times the result of z plus y, stored in a.
And expressions in computer programming follow the same rules that you learn in basic algebra.
Yep.
Which is please excuse my dear Aunt Sally, order of operations. Keep that in mind when writing your expressions, because you can get bit if you're not paying attention to this.
The next is introducing the function expression. A function is something that will be called to perform an action. So it's kind of like the expression, all encapsulated into a label. We have the function, what we want to call the function, variables that we pass into the function, and then inside the curly braces is going to be the block of instructions, and then the return statement returns back what the result of this function is.
Exactly. One of the things that we haven't discussed, and now would be a great time, would be the concept of a block of code. And if you look at this function here, there's a start curly brace directly below the word function, and then a close curly brace as the very last character. In the pseudocode that Brian and I use, this indicates a block of code, meaning this code is sectioned off as this. And we will see this when we get into C, and it's going to become extremely relevant. So just as a basic, understand that concept.
Right. So what's between the curly braces belongs to the function that we're referring to.
Right. Exactly.
So now we'll take a look at an example of a function.
Hey, look at this.
So this will be a basic power function.
Sort of like the one that we did in the
flowchart.
The flowchart example.
Absolutely.
Yeah.
So in this case, just like we described before, we say we're now going to define a function. We're going to call the function power, and we're going to pass the value of x and y.
Does this look familiar to you guys? I hope so.
Between these curly braces is the code that belongs to execute this function. So later on, when we just say power value value, this is what happens inside these curly braces.
And if you notice, we just have a little section that says do power process. Note that, because we will do the power process coming up after we explain a couple other structures. Here's how we call a function in our pseudocode. We just designate the function name, and inside of parentheses, we send the list of arguments that we're passing to the function. And when we take a look at this very next slide, here's an implementation of calling the power function that we have created back in the flowchart example, where we set our base equal to 3, our exponent equal to 4. And then answer will equal the power function and the list of arguments, which is base, comma, exponent. And inside of our power function, when we go back a slide, you'll see that we don't call x and y base and exponent, because it doesn't really matter what the variables are named local to this function. The variables have a different name when we're calling it, so it doesn't really matter what the names of the variables are.
Another element of pseudocode is going to be the decision statements. So things like if-else decisions. We went over the if-else in the flowchart, and just in the same way that we did, it's just a decision from a Boolean expression. If this is equal to that. If this is less than that. If something is true, then do something. Else, do something else.
Or else, if something else is true, do
Yes.
something else.
And so on.
Here are some examples, and actually, we've already kind of previewed this in other videos, but here's some examples of some decision statements in pseudocode. If condition, and then in the block, instructions. If condition, block instructions, else instructions. If condition, instructions, else if condition, instructions, and then else, other instructions.
So it's pretty self-explanatory. So that's the basic nature. Those curly braces show a block that belongs to the decision statement. So if the belonging curly braces, what to do if that condition happens. Otherwise, if this condition, what to do if that condition happens. Otherwise, everything else. Now we look at some more decision statements. You can have multiple conditions in an if statement. So you can say, if this condition is true, and, as you see with the double ampersands, this other condition is true. So if this and this, then do that. And then the one below that is if exclamation point condition means not this condition, then do the following instructions. Then is if a condition, and then within that if block, if another condition, then do these instructions.
Now that's in the bottom left-hand box. That is an example of what's called a nested if statement. And it's just simply an if statement that is inside a code block of another if statement.
And now we look to the top right, and this is the OR statement. This is with two vertical bars, dictates the OR. If, condition, or another condition, do the instructions.
Yeah.
And we can combine the two of these, so we have the AND is the double ampersand, and the OR is the two vertical bars. So if, condition, or, double vertical bar, condition, and another condition, then do these instructions. Now, that just goes in the order that we see it. So if this condition, or this condition, and this condition. Now in the bottom right with the parentheses, now we do it in order of operations. So if this condition and that condition, or separately from the result of that, this other condition, then do these instructions.
Now this is where practicing your basic logic will help, because when you're developing code, you need to define very strictly the types of conditions that need to be met in order for your program to flow properly. And when designing these conditions, keep in mind that condition statements or expressions must be a yes or no type expression, or true and false. So an example of this would be, does x equal y?
So let's take a look, a further example of using the power function and a decision statement. So you start out with the base is 3, the exponent is 4, and the answer is going to be stored as the result of the power function passing the base is 3 and the exponent is 4. So that's going to be 3 to the power of 4.
And then after we get this answer, we're going to do some logic. We're going to say, if the answer, so if 3 to the power of 4 is greater than 10, we're going to print to the user, answer, which in this case, in our pseudocode is going to be the number, is greater than 10. Now let's say that condition is false. Then we will fall through to the next condition. Else if answer is greater than or equal to 5, and answer is less than or equal to 9, which will set the values as either 5, 6, 7, 8, or 9. Then we will print to the user, answer is between 5 and 9. Now if that is false, we fall through to the next statement, which is the else statement, which is the catch-all. If everything else is false, then do this. And we just simply say that the answer is less than 5.
Very good.
Oh, why, thank you.
Now we move into the loop structure. So in the core concepts, we went over the concept of looping, while loops, these kind of things, and we saw this in the flowcharts. Now we're going to see it in pseudocode, and we're going to basically denote this by saying, while a condition is true, do what's in this block of code. And every time the set of instructions are run, then we go back to the top, and if the condition is still true, we run the block again. And we keep repeating that block of code until the condition is false.
So here's a pseudocode representation of that flowchart that we did before, that power function, where we have the while condition, so while c is less than y, increment the counter, and then set our answer equal to a times x, and then once we're done, we return the answer back to the user.
The next type of loop is a do while, which we've seen before. And so the do while is very similar to the while, but we do the instructions first and then test the condition. So the way we denote this in pseudocode is by saying do the following block of code with the instructions while this condition is true. If this condition is still true, we go back to the do and execute the block of code again until that condition is false.
So here's kind of an example of doing a do-while loop where we set x equal to 1, y equal to 10, and then we print to the user the value of x and increment x. So while x is less than or equal to y, which is 10, repeat this loop. Now you can see the important thing to note here is that x is consistently increasing, and x is also being used in our decision statement below. So once x equals 10, this statement is no longer true, and then we have printed to the user 1 to 10.
So here's the next type of loop, which is the for loop. And we've also discussed this before, and here's our pseudocode representation of that. The for is a constrained while loop. So we say for the start expression, let's say I is equal to 1, or the counter is equal to 1. A condition, that I is less than 10. And an iterate expression is the increment. So I is equal to I plus 1. The start expression, the number, the variable that we start with, our initial value. The condition of when that value is met. And the iterate expression is every time we pass this loop, do this to that value.
So as we kind of described before, you can do the same exact structure with a while or do while, but The for loop contains everything together. So when you look at a while loop and you see while condition is true, the for loop has that exact same thing. It's the middle condition. So the middle condition is what's being evaluated each time that the loop iterates.
So this might be clearer in an example.
Yep, here we go. Check this out. Brian, what is this?
So here's an example of a for loop where we set y to 10, and then just like we showed before, we write for, and then in parentheses, x is equal to 1, and that's the starting value. Then the condition that we test, x is less than equal to y. And you'll start seeing this looks just like our do while example. And then x plus plus means increment by one value. So every time this runs, x starts as 1, and then it'll be 2, 3, 4, and so on. And then within the block of code, what we do every time we loop through this is we print x. So this will start out as 1, and we'll print 1. It'll increment x plus plus, it'll print 2, print 3, print 4, print 5, and so on until x is incremented to 11. Mm-hmm. When x is incremented to 11, we'll evaluate is x less than or equal to y. No, it's not. We'll break out of it and not print.
So this for loop performs the exact same operation that the do while loop did that we just looked at.
Exactly.
Brian and I wanted to demonstrate a process where we build a flowchart, convert it to pseudocode. And we thought that a really fun example would be a basic sorting algorithm. Now, before I get any crap from people, yeah, this is a horribly inefficient sorting algorithm and you should never use it for any circumstance except for as a learning tool. It's a simple swap sort. Do your research. It's the worst algorithm that exists. But it's the easiest to explain to someone that's just entering software development. If you look on the right section where we have our list, this is our array. We have an array and the values are 1, 2, and 0. And we want this to be ordered from 0, 1 to 2. So what I want to do is just kind of walk through this algorithm, and we'll just kind of go through step by step, and then we'll port this into pseudocode. So the first thing that we do is we take our list in. So the required parameters is the actual list itself. Then we start our data off as setting I equal to 0. You guys can kind of see this kind of has the structure of a for loop. Keep that in mind. And the length of our array is going to equal 3 because there's 3 items in the array. So once we've gotten through this section, we're going to go to our decision. Is I less than length minus 1? So is 0 less than 2? In this case, the answer is yes. So we fall over here to the yes condition. Now we're going to evaluate, does the current item that we're looking at, is that greater than the next item in the list? So in this case, it's not because 1 and 2 are already in order. We're actually going to fall into the no condition here, which increments I. So then I will equal 1. We come back now into the decision structure. You guys can see how this loop is forming. Now I equals 1, length still equals 3. Is I less than 2? Yes. Okay, let's fall to the next condition. So basically what we're saying is we have not reached the end of the list. In this condition, is the current value greater than the next value? And the answer now is yes, because you could see that 2 is greater than 0. So what do? We perform a swap operation. The swap operation is simply storing one value in an array, setting that value equal to the next value, and then resetting the current value to the stored value.
So we'll use the temp variable as a placeholder to hold the value that we overwrite. So where 0 is, we hold it in a temporary holding place, and we copy 2 up to 1. So now it's 1, 2, 2, and then we take from the holding place 0 and put it back to 2.
So now if you look on the upper right where we have the yellow text, you can see that 0 and 2 have been swapped. So now 0 has been moved above 2. And now we're going to set the incrementer back to -1. Now, for those of you that may be confused, you'll see at the next operation, we increment I. So even though we set it equal to -1, when we go back to our iteration, we set it back equal to 0. So now we're going to the top of the list to reevaluate it.
So in other words, every time we perform a swap operation, we start all over again in the list.
Yep, exactly. Which is why this is a horribly inefficient algorithm. All right, Brian, let's take us through the next set.
Now I is set to 0, and we're going to run through this again. So now we check the decision. So I is 0. Is it less than the length minus 1, which is 2? Yes, it is. So now we're going to drop down to the bottom, and we're going to evaluate the contents of those positions. Is the current position, which is 0, greater than the next position, which is 1? 1 is greater than 0, so that falls into the yes condition. Now we're going to perform another swap operation. So we're going to temporarily store the value off and switch it. So we're going to swap 0 and 1.
So now look at the list, guys. The list is actually in order now.
Yes. Now, because we've performed a swap operation, we've set the incrementer back to 0, and we're going to start this whole thing over again. We test this and say, is 0 less than the length? It is. So now we evaluate to see if they're in order. Is 0 greater than 1? No, it's not, so we go to the next one because they're in order. So we increment, we check to see if we're at the end of the list. We're not, we go to the next one, and we see if they're in order. Is this one greater than the next one? No, it's not, they're in order. We go back. Are we at the end of the list? Is 2 less than the length minus 1, 2? No, it's not. So now we're going to hit the note condition because we're at the end of the list. We've not performed any swap operations, and everything seems to be in order. So now we're going to return the array in its sorted form.
How cool is that?
Done.
So now that we've gone through this algorithm as a flowchart, Brian, what do we have here?
Pseudocode.
Oh, we have the swap sort operation in pseudocode. Let's kind of walk through one at a time so that we kind of understand how we convert the diagram on the left to the code on the right. As you can see, the function is called sort, and we have labeled the function here, function sort. And over here we have the parameter. So what we say in our pseudocode here is the required parameter is ARR, which represents the array that we're passing.
The unsorted array.
The unsorted array, the input data. So Brian, what happens here?
So now we check the length of the array. So we're calling another function, a predefined function called length.
Yeah, just pretend like we've already written that.
And a lot of times in pseudocode, if you call a function that's not defined, you can just assume that some function like that exists that will return what you're looking for.
Mm-hmm.
So something like length, count, substring, things like that will generally just assume that you don't have to write that yourself. So the length will return the length of the array. And we're going to store that in the variable length. Also, you can see in the starting position of the for loop that we initialize the variable I to 0, just like we've done before. The next part of the flowchart, you can see that I less than length minus 1 is going to be our condition of the for loop. So that goes into the middle between the semicolons. Just as you can see in the middle of the for, I is less than length minus 1. And then at the end of the for loop, there's the I++. And that
which we don't get to yet.
Right.
That increment happens after we've gone through the loop. So you can see the flow of a for loop is I check the condition here. If this condition is true, continue on. That incrementer operation happens after the iteration is done.
Right. We now evaluate the contents. If the contents of array position I, which is 0, is greater than array contents at position I+1, do the following block of code. In the yes or no of the flowchart, the yes path goes inside this block of code. The no path would skip this block of code.
And go to the next iteration.
Right. Because there's no other code left at the end of the for loop.
Which we'll get to. We're going to take this the whole way through.
This, inside of this if condition, is our swap statement.
So our swap statement, like we described before, we're just going to be storing the values and setting I to 0 or to -1. But the important thing to understand is this little box fits in this little box on the right. So this little box represents our block of code that belongs to the if statement that came before it.
Right.
Now, once this condition has been evaluated and either processed or skipped based on the if condition above, we drop into the incrementer, which happens here, I equals I+1, or it's also expressed in this case as I++. So we've actually gone through one iteration of the for loop where the condition is true. Now, what happens when we come back to this condition and evaluate it and it's false? Well, first off, you can see that we go from the incrementer statement immediately to the condition statement. Now let's go through the scenario where this condition is no longer true. Well, we drop to this return. And you can see on the bottom of our pseudocode, we're returning ARR, which equals the value of the sorted list.
So that's a pretty fast and dirty walkthrough of translating a flow diagram to pseudocode. Mm-hmm. And there's really not that big of a leap.
No, it's not.
So I hope that helps you to bridge the gap between those two.
Yes, and pay attention to this, guys, because when you get good at this, you're going to be amazed at how easy your transition to C is going to be.
You can do a lot of these as exercises. You can make a flow diagram of how to start a car and try to put it into pseudocode. You can anything that you do, you can try for yourself to make up a flow diagram and just try putting it into pseudocode for practice.
Yep. All right, thanks, guys. We'll see you in the next video. In this video, we're going to be talking about integrated development environments, also known as
IDEs.
So, Brian, could you please explain to me, with your massive intellect, what an IDE actually is?
An integrated development environment.
Okay, that's the end of the video. Thanks for watching.
So an IDE
Oh, wait, there's more.
An IDE is basically the application, the software that you use to write a program. Now, some time ago, writing a program didn't really require all-in-one program. You would use a text editor. After the text editor is used to type out the file, save the file, goes to compiler. Then after the compiler is run, you do a build automation. Sometimes you have a GUI tool for graphical user interface stuff. You'd have a debugger if you have a problem with your code. You have separate tools and programs to check for memory leaks. So now we've taken all of those programs and put them all together in one, which is considered the IDE. So although sometimes an IDE is used for, like Visual Studio, for example, is an IDE used for particular languages, some are more generic, like Eclipse.
Yeah, because Eclipse you can use multiple languages.
It's basically like a portal for all of your development programs. So we're gonna kind of take a look at these and look to see why they're so important.
Now, Bryan made a comment that it used to be a text editor and a compiler. Now, I will disagree with Bryan there because in many instances I will still use a text editor and a compiler, and it is. For some things, that's great. And it's great for learning because when you start using IDEs, it's kind of important for you to see, well, what is the IDE actually doing? And you won't really appreciate what IDEs do unless you get involved in this sort of thing, which is like build compilation procedures that are more complicated than they really have to be. And we may later do some examples with this where we're actually compiling a program using make, install, which isn't that complicated, but it's more complicated than it has to be.
It's more than one click of a button.
Yeah, well, yes. And if you run through make and it says, oh, well, this is missing, or the path of this file is incorrect, or your libraries are in the wrong directory, that could be a pain in the butt to go through and edit.
And it just burns your time, your valuable time as a developer. Just,
Yeah.
It makes you not quite as efficient.
So it puts everything you need in one place. Like Bryan said, every little piece of tool that you need, an ASCII text editor and a compiler, build procedures and that kind of thing, is all in one application. It also simplifies project distribution. So instead of me taking 50,000 pieces of source code and emailing it to someone and saying, hey, here's like a 5-page compilation procedure that you need to do this, I can just zip up my project file or my project directory and send it to you, and you can open up on your machine.
They will also integrate with source control programs.
Yeah, right.
Like Vault and Subversion and whatever. So that if you're developing with other people, that packaging up of the source code also packages up and distributes among the other developers. So you can see if somebody else is working on or modified a file or whatever the case is.
It's also kind of cool with automatic version control, where build counts are stored, so when you can look back at your different versions. Many IDEs make it very easy to publish your applications. Like Visual Studio, you can have setup projects that do installation programs for your software. So if you build a service, you don't actually have to go through the whole process of doing the install util. That just happens automatically through the IDE.
Right. Or if you're developing something for a website that's on a web server, you can, from the IDE, publish what you build to the web server. Or to another web server. Very
good point. Like when you're doing ASP, you actually publish it. Good point. Here's a sampling of some popular IDEs that are in relatively widespread use today. Now, some people may argue with a couple of these, but, this is our list. This is what we see. We see in the Windows environment, for the most part, Visual Studio is the gold standard. And I will say, I'm not a big Windows homer. I do program in Windows a lot, and I do like Windows. I will say Visual Studio is probably the best development tool that I've ever used.
Yeah, it's very nice.
And that's not to say that I don't like Unix and Linux. I love it. I love those platforms, but Visual Studio just Microsoft really has a leg up.
Right.
On pretty much most of the competition.
And you see that there's a lot of applications developed for Windows, not as many developed for Linux, not as many developed for the Mac. And one of the big reasons really comes down to Visual Studio.
Yeah.
Visual Studio is a key component in Microsoft's success.
Turbo C++ is also in widespread use. You see this in colleges a lot. Dev C++ is kind of dying, but it's sadly because I love Dev C++. But it's kind of a very basic C++ IDE, and it's great for developing C and C++ programs. And in Linux, Bryan, talk about what we have in Linux.
You have KDE Develop.
Or KDevelop.
And this is an IDE for the KDE shell in Linux. Then there's Anjuta, another open source Linux IDE for C++ and other languages.
It's very similar to Dev C++.
Yep. But not specifically tailored to KDE. So this is more commonly used for the GNOME shell. Then Sun Studio for Java and other languages like that.
Next we have the Mac OS There are more, but the exclusiveness is Xcode.
Yeah.
There is a version, actually KDE, there's actually a Mac, KDevelop, there's actually a Mac version of it. But its exclusive development studio is the Xcode
And
IDE.
that's generally what you'll find people using for Mac.
There are also IDEs that are multi-platform. So Eclipse, you'll find Eclipse for Mac, for Windows, for Linux. NetBeans, same thing. Mono, same thing. Now Mono Develop is great. That's the C#, the open source C# stuff. NetBeans is Java, and Eclipse is basically whatever you want. You can configure Eclipse to be an IDE for many, many different languages.
NetBeans seems to be pretty common for anything from BlackBerry development to web services. It's also not exclusively a Java IDE, but primarily that's usually what you'd see people using it for.
Here is a screenshot of the Xcode IDE for Mac. Now don't mind the code as much, but just take a look at these basic elements that we have. On the left portion, we have that project organization that we talked about before. So we can see that our program is set up. We have our source files here and our documentation here. So it's all in this little virtual directory structure. On the top, we have options for build and run. And as you can see on the right, I have this little green box that says, here is your ASCII text editor. So you can see that there are these three programs, or these three concepts combined into one program. And in the upper right-hand corner is the console. So when I execute the program, this is what the output is. So all of this is stuck inside of this Xcode IDE.
Now we go to the opposite end of the spectrum to a completely different IDE, Visual Studio. It's totally different. Absolutely different. As we can see, unlike the other one, we have the exact same debug, build, and run menu.
Yep.
The GUI tool or the ASCII editor basically in the same location, exactly the same thing. Mm-hmm. And then a project organization. So the biggest difference basically between Xcode and Visual Studio is that the project organization is on the right side of the screen.
Yeah. Next we have KDevelop. Now what's really different between KDevelop and the other two? Not really that much.
But the project organization is back on the left side of the screen.
And we also have our run and debug options and our ASCII text editor. Of course, we have many other things like memory tools, but you can see that there's a trend here. They all kind of look the same. Now, this also kind of stems from the birth of the original integrated development environments, which we love QBasic. When we were little kids, Brian and I loved QBasic. It was our favorite thing in the world.
This is the first IDE that we've ever used.
And it's also one of the early ones, because it wasn't really until the 80s that you started seeing this.
Yeah.
So how does this differ from the other two? Not much. We still have our build, and we still have our ASCII text editor. The only thing we don't have is project organization, but at the time in the 90s and late 80s, code wasn't as complicated then, so it wasn't needed. Mm-hmm. But you can kind of see that even going back to the 90s up until now, the only thing that's changed is it looks prettier. But the functions are still there.
Absolutely. Welcome everybody to our video on variables, data types, and formulas.
Woohoo!
So this video is going to be just a basic overview of these concepts so that when we come across them later, you'll understand what we're getting at when we say int and char and string and the rest of them. So what is a variable?
I don't know. What is a variable?
We'll start there. A variable is a symbolic name that represents a value within a computer program.
Interesting.
So in other words, it's a label applied to a location in memory where we store some value. So how do we declare a variable? Well, each variable has a name or a label applied to that variable. That name can only be certain types of characters, certain types of legal characters, like a capital A through capital Z, lowercase a through lowercase c, 0 through 9, and an underscore. But also, a variable label cannot start with a number. It has to start with a letter. And it cannot contain spaces.
Yes, but it can start with an underscore if you want it to.
That's true.
Yes. So here are some examples of some legal variable names, or here's an example of a legal variable name. Variable 123. And below we have two illegal names, which is 123 variable and variable space 123. Now this is pretty consistent across almost every language. You can't start with numbers.
Yep.
So that's generally, even though this is not specific to a language, it's generally good to not start with a variable with numbers. In computer programming or in software engineering, we deal with two types of data types. Now we've sort of brushed on primitive data types, but just to kind of solidify your understanding, primitive data type is like a building block data type. It's something that is supported by default in the programming language. For most languages, it's and that's why they call it primitive. It's the most primitive form of data storage, and that's a number. Anything that can be expressed as a number is a primitive data type. That's why you have things like integers, characters, floating point, other things like even strings are technically numbers. And some languages treat strings as native, some don't. We also have composite, which Brian will tell us about.
So a composite data type is something that is composed of multiple primitive data types. These can also contain other composite data types as well. So it's a data type that incorporates other data types, basically. These you'll find in structures and unions and classes, which we'll get into later. There's also the idea of things being signed versus unsigned. So in primitive data type instances where storing a number, a signed data type is going to be both a positive and a negative number. So negative 100 or positive 5,000. An unsigned data type is where it's only positive numbers. So we don't have the negative property. It's just 0 and above.
Yeah, so you actually allocate the same amount of memory in both cases. But if you're doing something like a 16-bit integer where you have 65,000 potential values. In a signed 16-bit integer, you go from like negative 32 to positive 32. And unsigned, you go from 0 to 65,000.
So unsigned data types usually are used in circumstances where you have a math formula that's dealing with very large numbers. A lot of times if you're looking for a large prime number, or sometimes in cryptography, you're dealing in a circumstance where it's not going to be a negative, but the number is going to be extremely large.
And sometimes in cryptography, the numbers you're dealing with are so large, you actually have to import other libraries that manage numbers of that size.
Because they go well beyond unsigned.
Yeah. So here's a chart that has some common primitive data types that are pretty much consistent across most programming languages. The integer data type consumes about 4 bytes. We also have here the unsigned and signed ranges, which I'm not going to talk about because that's like billions and trillions, and I don't feel like talking about that. The short integer, which is a smaller subtype of the integer, it's 2 bytes, which for those of you that are counting, that's 16 bits. We also have characters, which are 1 byte, and most languages don't allow these to be negative, so we're usually dealing in this positive range. Strings are similar to chars, except for its variables. So a string is a sequence of characters. So this can be 1 byte to as many characters as you have in a string. A Boolean is technically an integer. It's a 1 byte integer that stores either a 1 or a 0. 1 would signify true and 0 would signify false. The float type stores typically about 4 bytes, and it's accurate within 7 significant figures. In mathematics, significant figures basically talks about the preciseness of a number. So it's 7. Usually that means like 7 decimal places. A double is double the size of the float, so that's an 8-byte value, which is usually accurate within 15 significant figures.
So now we'll take a look at our first data type, which is the integer. The integer is a number. This number can be a Boolean data type, which is 4-bit. It can be a byte, which is 8 bits. Short integer, 16 bits. Integer, 32 bits, which is the most common that you'll be using. And a long integer, 64 bits.
Do me a favor. Will you say that unsigned long integer number for me real quick? I'll give you $50. I'm kidding. I'm not going to pay you. Look how big that number is.
Okay.
Do you
How
even
about
know?
this? I got it.
You
Ready?
got it? Okay.
18 446
No!
No, hold on. 073 709 551 615 E minus 18.
You are a cheating. Alright, I'm sorry. I interrupted you.
You didn't say I couldn't use scientific notation. So most often you'll use the 32-bit integer, but in some circumstances you're going to use the long integer. There's no decimal place, there's no precision point in integers. It's just a whole number.
And the floating point is the opposite, I suppose. It's a rational number, or a real number in mathematics. It could be floating point, which is a 32-bit number, usually accurate within 6 or 7 significant figures. So in this case, if we have 2/3, you would have this many decimal places. 64-bit floating point typically is called a double, which is usually accurate within 15 significant figures. So 2/3 as a double would store this much precision. And some languages support a more advanced floating point, which is a decimal. Now this is sometimes between 96 and 128 bits. So you can see how much more precise that this number is. And even though this doesn't look like a lot, you look at the float and the decimal. Let's say if you were shooting a rocket towards the moon and you were using floating point numbers, by the time that you got to the moon, that offness and precision could actually have you missing the moon at that distance.
Or like completely missing the moon by 4 moon length stat.
Yeah, exactly.
No.
So precision, especially when you're dealing with science,
Oh, yeah.
and it's extremely important.
Well, you have to consider that when the shuttle docks with the space station, for example, that's like throwing a baseball from New York to like a basketball-sized hoop in France and hitting that target. I mean,
Right.
it's crazy.
You have to be very precise. So maybe the decimal's not even precise enough.
Yeah. And the next is the character data type. So the character data type is just a single letter. Generally in ASCII, this is 8 bits, and Unicode is 16 bits. ASCII will give you the range of 0 to 255 and includes the standard characters like lowercase a through z and uppercase a through z, a white space, new line, tab, tildes, those kind of things. In Unicode, depending on the standard, you'll have some other types of characters and symbols like the strange mu symbol or the, whatever.
Yin.
Yeah,
that kind
exactly.
of thing, yeah.
They're strange Hebrew symbols that I have no idea what they're for.
Yeah, and why they're like, when you go to Microsoft Word and you go to symbols, why is it the first thing you see?
Yeah, it's A, B, C, D, E, F star, David. Where did that come from? Oh, well, that's cool.
I mentioned strings as primitive data types. In some languages, technically, strings are not a primitive data type. They are a composite data type. But some languages like Perl, TCL, strings are primitive data types. So in languages that support strings as a primitive data type, it is just simply a sequence of characters. So this sentence here, this is a string. You can see those are just characters put together as one sentence. And that's just what a string is. So Brian talked about composite data types before. Now it's my turn. I get the pretty picture slide, so I'm the lucky one. So kind of like when we talked about objects before, a composite data type can be an object, like when we talked about the person. For the most part, in what we're going to be talking about later in C, they're actually a little more simpler than that. So if I have a student data type that I want to create, and I want to attach these 3 things to my student, I want him to have a string that's his name, a string that's his major, and an integer that is the student ID. I can then attach these to my student, and I've created a composite data type, which, as Brian said before, is a collection of primitive data types or other composite data types.
So in the case of the student ID, it's considered to be the integer data type. So when we store a value in the student ID, we store a number. So when we go to store a value to student, we store the value to the student name, major, and student ID.
Right.
When that's created.
Yep.
So now we'll take a look at the basic math operators of the C language, and in turn, most languages that we'll find.
You'll find a couple
of
of outliers. Like, I think BASIC has a few things that are
BASIC always has outliers. Yeah. I mean, whenever. So most of the operation symbols will be pretty intuitive to you. I'm sure naturally you're going to see the plus symbol and you're going to assume addition. It's the same symbol that you use in mathematics. So you see the plus symbol, it's addition operation. You see the minus symbol, it's subtraction operation. The asterisk, since it looks the most similar to the multiply symbol in mathematics, is multiplication.
Yeah, and we can't use the X for times because that could be a variable.
Absolutely. The / is used for division, and the percent symbol is actually used for modulus. So let's see some examples of these used in expressions. So if we were to evaluate the expression 1 addition symbol 2, it would result in 3. 1 plus 2 is 3. With the multiplication symbol or the asterisk, 100 asterisk 3 results in 300, because 100 times 3. In the / you see 10 divided by 2. So the / is slashing to the right. So the number that appears to be on top is divided by the number that appears to be below on the right. And in this case, 10 divided by 2 is 5. Next is the modulus symbol. So if we have 5 modulus 2, the value is 1. So for those of you who don't know modulus is the resulting number after the number on the right has been divided by the number on the left.
Yeah.
So that's a strange way to say it. So in this case, we say 5 modulus 2. Well, 2, 4, and then the next number is 6, which is greater than 5. So we stop at 4, and we have a remainder of 1. So 1 is the result.
Another way to calculate modulus would be to do 5 divided by 2, which is 2.5, and take the decimal point, which is 0.5, multiply that by the divisor, which is 2.
There you go.
So 0.5 times 2 is 1. And you'll find that is true in all modulus and all division types. And I think mathematically that's for me anyway, it's a simple way of calculating modulus.
And if we confused you even more, just go to Wikipedia and search for modulus. We spelled it for you up above.
Oh wait, I don't know. Have you seen the Wikipedia, like, give me money things on the website? Yeah. Maybe Wikipedia won't be around in a couple weeks.
Well, I think they will because they're so f***ing intense. You know, that guy's like, this is a call to arms.
It's call to arms. Have you seen in every picture of him too? He's like sitting there and he looks all like serious.
That's intense,
and,
yeah. Like, I'm just, every time I go to Wikipedia, I'm just terrified that
we must all rise as a nation. It's the both Wikipedia.
this is not madness, this is Wikipedia. Whatever, I'm sorry. So lastly, the minus expression, 1 minus 10 results in a negative number, which is 9.
So here's some of the comparison operators. We've sort of brushed on these, but just to kind of officially state, typically the double equals is an equal comparison, whereas a single equals is, I think it's called like a set operator. So the double equal says on the left expression and the right expression, are they equal? And the exclamation point equal is not equal. So not, exclamation point typically means not equal. The less than, you remember that, the Pac-Man goes towards the bigger number. Less than, then less than equal to, greater than equal to.
Now the not equal symbol, the bang equals, exclamation point equals, generally speaking is in most languages, but this is the symbol that sometimes varies from language to language. Sometimes this is represented as a less than greater than.
Yep. Like in SQL, it's like that.
Right.
Some SQL implementations. There's also
and basic and
like Perl is like NE.
Yes.
And also Perl equals EQ. Mm-hmm. So some languages it does vary.
But for the most part, this is what you'll find.
Mm-hmm. And also the double equals is valid in some Perl expressions, but I think it's when you're evaluating strings that you have to use EQ. So it can kind of go both ways. So as we talked about in the last slide, here's some examples of some comparison expressions. Does 3 equal 3? Well, if you look in the right column, that's false, because that's not a true statement. 2 times 2, which is 4, is less than 1 divided by 2, which is 0.5. Well, that's just flat wrong. That's false. That is not a true statement.
Obviously.
So now we have 9, now order of operations, people. 9 times 1, which is 9 minus 3. So that will be 6, right? 6, 7, 8, 9. Perfect. So 6 is less than or equal to 7 minus 1, which is 6. That is a true statement, so it's true. 2 mod 2 is less than 2. That is also a true statement because 2 mod 2 is 0. Because remember our example from before, when you divide 2 into 2, it's 1.0. 0.0 times 2 is 0. There's your modulus. Next, we have 1 plus 4, which is 5 is less than or equal to 100. Looks true to me. And next we have 2 times 10, which is 20, does not equal 20, and that's just flat wrong. I can't even believe that I actually typed that. So there are some examples of using some comparison operators.
Lastly, we have logical operators, and we have the OR and the AND operation. So the double bar symbol is the OR operation, and the double ampersand symbol is the AND. So in this case, we have if truth, or something and something. So let's look at some comparison expressions. Here we have 10 equivalent to 5, which is false, or 10 less than 100, which is true. So in this case, it's either false or true, and since it's an OR operator, only one of them must be true, so the final comparison result value is true. And you can see that on the right with the false or true results in true. In the second condition, we use the AND operator. So 10 equivalent to 5 is false, ampersand, or and in parentheses, 10 is less than 100, which is true. So in this case, we have false and true, which, because it's the AND operation, we need a truth and a truth. So this results in a false value.
Just as a heads up, when looking at this, pay close attention to our bitwise video, because of these bitwise expressions directly relate to how computers make these decisions.
Absolutely. So at this point, you should really know how the OR and AND function. But for this language and a lot of other languages, the OR is the double vertical bar and the AND is the double ampersand. So now we get into formulas. The sole purpose we get into programming.
Yes.
In order to take a formula and translate it to a program.
Yes.
So that we don't have to do the formula again.
Absolutely. Do we just take it from the top?
Yep.
Let's do it.
So on the left, we'll see the classic formula of x equals 3 times 10.
But it's an x.
Yes.
3x10.
X symbol.
That's not like a computer time sign.
Right,
What do we
that's
do?
the math symbol.
Yeah.
So, well, as we learned, the x symbol is really the asterisk symbol.
Yeah.
So, x equals 3 asterisk 10. And that's our formula. It's that simple. So we're just swapping the operator in that case.
What do we do in the case of a 2 over 3 times 100?
Well, we lay it out and do the order of operations. So in this case, it's basically the same thing. We want to evaluate 2/3 first. So we say x equals, and then in parentheses, 2/3, which looks pretty much the same if you just kind of tilt the 2 over 3 to the left a little, multiplied by 100. So inside the parentheses will be evaluated first, then the multiplier operation against the 100 will be stored as x.
Although technically speaking, in order of operations, the parentheses are not necessary, but for aesthetics it's there, because with order of operations, that would actually read from left to right. But it's good practice. Parentheses are always good. Now, next, this is a little bit more complicated to explain, and we'll do our very best to simplify it. When you do something to the power of something, a lot of languages have their own way of doing this. There are some languages that allow you to simply do, if you're doing x equals 10 squared, 10 caret 2 to symbol to the power of a number. However, there are a fair amount of languages that don't allow this functionality because the caret is reserved for other functionality, and you're forced to use functions or classes to do this. So in some languages, you may have a power function like we created before, where you pass the lower number 10 to the power of 2. We also have that same exact situation below, where we have the square root of 10. Well, the square root of 10 is actually 10 to the power of 1/2. Now, there are some languages, like I think C has an SQRT function that does a square root, but when you're doing a square root, that's what you're doing. Power of 1/2. So in this case, we have 10 caret 1/2 for languages that would support this syntax, or other languages that don't, that use functions. We would say use the power function for that language, 10, 1/2. Now Brian gets this nice, fun, little complicated one here.
Nice. Okay, and this last function is going to be the calculation of the area of a trapezoid.
We think. We hope.
Probably. Which is a is equal to the base plus the other base times height over 2. So, to translate this, we just kind of march through it from top to bottom, and we say, let's take the top half first, and say the inner parentheses, the uppercase b plus lowercase b, just like it is in the formula, in parentheses, multiply symbol, lowercase h. So we're assuming we've already stored these variables beforehand, that they have values, and then we encase that entire thing in parentheses. So now we have a parenthesis before the b plus b and after the h. After we've encompassed that upper half of the formula, that we then say /2 to divide by 2. So that effectively reads, a is equal to the value of b plus b times h, all divided by 2.
Now, unlike the other formula where the parentheses technically didn't matter, in this one in this case the parentheses absolutely matter. Without those parentheses, you get the complete wrong answer.
That's true.
So, order of operations, people. Now let's take a look at a little bit more of a fun formula here. Now I believe this is a quadratic formula, or a quadratic equation.
Hey,
this isn't the quadratic formula.
Right.
This is a quadratic equation where you have ax to the power of 2 plus b x plus c. So everything is kind of like moving down. Mm-hmm. So in this case, we're going to do
binomial.
Whatever. You're probably right. Mm. I haven't been in algebra in a long time. Z equals a times the power of x to the power of 2 plus b asterisk x plus c. So let's kind of walk through this real quick. Here's the a times x to the power of 2. So we translate that by separating it with an asterisk. Now, since we don't really need to separate this with order of operations, the power function will actually be evaluated first in this case, and then the a times will be for order of operations, and this would naturally happen in the program flow. And, of course, here we have the power function. Then right here, b times x, which will be evaluated next. And then we have c here. And then after that, the value of those expressions will then be added to equal z. Now here is the quadratic formula.
There you
go. Nice. Awesome. Okay. Now, Brian, and this might take two of us to walk through.
Okay.
How about you start, and when you give up or get tired, you call me. Send me a text.
So we can visibly break down how we're gonna lay out this formula. So we have the top half and the bottom half, where the whole result is divided by something else, by 2a. And above that, we have everything that's in the square root, and we have everything that precedes the square root. So we can just march through it left to right. So we're going to store x as being the value of negative b plus, and now since the square root function is effectively a power function, we say the power of the result of the inside to 1/2. So by saying the power of the result of b squared minus 4ac to the power of 1/2, that's effectively saying the square root of. Mm-hmm. So negative b plus the power to the negative 1/2 of b to the power of 2, which we see is power paren b comma 2. So b to the power of 2 minus 4 times a times c. So in the order of operations, I think that'll just go left to right. So we'll have the power function we'll evaluate first, power b to the power of 2, then 4 times a times c,
Yep.
and then those will be subtracted from each other, which will result in the value that's calculated by power to the power of 1/2. And lastly, that gets added to negative b. Once that has been performed and evaluated, then it continues on to the forward slash and evaluates the 2 times the a, and the result of that is divided into the result of the upper half.
So, Brian, that was quite a mouthful.
Yes.
And you know, we don't want to sugarcoat this. Computer programming is very math heavy. Sorry. There's no way to simplify that. So you have to kind of get your math order of operations under control if you want to continue in this. Hopefully we don't scare anybody with this, but it is important to understand. So maybe we can walk through this real quick since this is the most complicated formula we have here. So let's just see if maybe we can make you feel comfortable with this. So as Brian described, this is broken up into 2 halves. Obviously, we have something divided by something, 2 halves. So when we walk through this, negative b obviously is set up as this statement here. Then we also have the square roots, which as Brian so profoundly explained, is to the power of 1/2. Now the reason why we chose to use a power function here is because you're kind of on your own with a lot of languages when it comes to doing roots. And the reason why is because programming is so math heavy, the assumption is you already know this. So some languages do have a square root function, but what if you have to do to the 3/4, to a cube root? A lot of times that has to be a power function because it doesn't contain that functionality natively. So we have that power. Then we have b to the power of 2, which is this here, minus 4 times a times c, which is this value here. And then lastly, the second chunk of this, we divide it by 2 times a.
And to be honest, if we go over this many times and you're still having a tough time getting it, maybe doing something else would benefit you.
Yeah, or just pick up a math book and come back to this.
There you go. So here's typecasting. Typecasting is effectively taking a data type and make-believing that it is a different but similar data type.
Yes.
So for example, if we have an integer value and we typecast it as a float value, although we're still storing the actual integer value, we're now going to interact with it as if it was a float value. And so that's typecasting. So when you deal with variables, you are going to be dealing with a lot of different types of variables, and you won't always be able to stick with the same data type. You might have to move from data type to data type.
Now, there's also a different form of conversion that's way more advanced than typecasting, which we're not going to even get into in the introduction videos. When we get into programming videos, we'll visit that topic then. So let's kind of look at an example of where typecasting is actually used. So this is a practical typecast example, Brian. So we have integer x equals 4, integer y equals 10. Now I want to have a double value, which, as you guys remember, is a 32, a double-sized floating point value. So we have z equals y over x. So this is 10 divided by 4. Why does z equal 2, Brian? They don't divide into each other equally. There should be a decimal place here.
But the division operation is being applied to 2 integer values.
Really?
And then the integer value as a result of the division operation is being stored as the double.
Well, how do I correct this then?
Well, by typecasting the 2 integer values, obviously. So now in this case, which is different than having the integer divided by an integer and then the result be a solid number, which was 2, stored as a double value, 2.0 effectively. In this case, we're typecasting the integer value y and the integer value x as doubles. So now we have a floating point precision on the y and the x. So when the y is divided by the x, we have a precision with which to store the remainder. So the 10 divided by 4 gets resulted as 2.500 whatever, however much space we have. That result then gets stored as z, so z can maintain that precision of 2.5.
And one thing that's kind of interesting to note here is when we typecast these values, we're temporarily using them as doubles.
Right.
So we're saying take y and just pretend it's a double.
Right.
So we're not actually storing y as a double. We're saying in this instance, at this specific moment, pretend it's a double.
So effectively, after we've stored z to be 2.5, y is still an integer.
Yep, still an integer, sitting there collecting no decimal points. Now, an important thing, guys, really important. Declaring variables in languages is extremely different. And, well, I don't want to say extremely different. A lot of it's the same, but there are a lot of things that are different. So let's take a look at a few languages and how we can declare variables in them. And we'll first look at our little baby here, C++. So in C++, Brian, these declarations look eerily similar to the ones in our pseudocode. I wonder why that is. So in C++, we would declare an integer by saying int, which is short for integer, the name of the variable, and then the value. Character, char, short for character. C, which is the name of our variable, equals single quote S single quote. You find in most languages the single quote represents a character, whereas the double quote in the next example is indicative of a string. So string word equals quote hello quote.
So generally speaking, when you see single quotes, you won't see more than one character between them.
And if you do, some languages like SQL are okay with that, but
not often.
Yeah, it's not that often. Perl does that, but not often. You're right. Bool is true equals true. In some languages, you would actually have a 0 or a 1 value. In most languages, you can just say true or say false. Double pi equals 3.14. So let's take a look at these exact same variable declarations in a language called Visual Basic, which I think, from reading the scripts from the earlier videos, I think this is your favorite language, right?
Yeah, probably. Yeah.
Like, you love this language more than anything in the world.
I think this is the language of the future.
It is now 1991.
Our favorite language.
Your favorite language, I think.
Visual Basic.
Don't you have a tattoo on your arm that says I heart VB?
I actually have... Visual is on one inner thigh, and Basic is on my other inner thigh.
And they're constantly loving each other.
Yes, exactly. So everywhere I walk, my two inner thighs are just gently grazing among each other. How's that for a visual image? Internet.
Wow.
Put that on YouTube and shove it.
I feel kind of sick, actually.
So, when we declare a variable in Visual Basic, we redundantly put dim in front of every one of these declarations. So we say dim number, which is what we're calling our variable in this case, as an integer, which is equal to, in this case, the number 1, 2, 3, 4. So dim, which this is not something that's intuitively understood, stands for dimension. And dimension was originally used in the earlier implementations of BASIC to define...
That was that Dartmouth?
Yeah, BASIC.
BASIC? That was like in the 60s or 70s? 70s.
So originally, dimension was fully spelled out, and it was used when declaring arrays. And the size an array would require in memory. So basically, dimension this dimension of the array in memory. Later, it just kind of became adopted to say dimension this into memory. Because the implementation of saying as an integer and as a character, as far as memory is concerned, tells the computer or the compiler how much memory to pre-allocate.
Right.
So we're basically dimensioning this amount of space. And how much space? Well, it depends on the data type. As an integer. So an integer requires whatever.
32 bits.
Yeah. So it's redundant. It's stupid. You have to just type dim. It's not dim sum. It's just dim.
Dim.
So dim, C as character, as char, equal to single quote.
Well, I think it's double quote.
Is it really?
I think it's double quote in VB.
Visual Basic, I hate you. Let me count the ways.
Do a quick Google on Visual Basic char.
Yep, you're right.
So, as we were talking before with the single quote, not so much with VB.
Yeah, well, Microsoft endorsed it, so not all rules apply.
And not all rules apply consistently.
There you go. Then we have dim, a variable called word, as string. And this is also double quote, hello, exclamation point. Dim is true as Boolean is true, and dim pi is double is... So like we've seen before...
Boy, am I glad that's over.
Yeah.
Now let's talk about some variable declarations in Perl, which couldn't be more beautiful.
Yes.
Now, Perl is a language that they like to treat all their data types very similarly. So you can like take one data type and make it another one without even having to do anything. So when I say I want to declare a number, just, okay, do it. Dollar number equals 1, 2, 3, 4.
Yeah,
and it's like,
It's like free love.
Yeah, so then I'm like, hey, Perl, I want to make a word. Yeah, just put quotes around it. That's cool. Whatever. Yeah. Hey, Perl, I want to make a Boolean. Yeah, what? Just shut up and just
do it.
Put true there. You don't have to ask it. You just do it.
Just stick it in there.
That's why I like Perl and PHP.
It's like the hippie language. It's awesome.
Now let's take a look at something a little different. TCL, which is a little bit more, but not nearly as annoying as VB.
But it's similar in the sense that you don't declare the type of variable.
Yeah, that's true.
You just set a number as this. You set the word as that. You set is true to 1 for true, or 0 is false.
Yeah, you set pi as 3.14.
And so it will naturally see that you used a decimal point in pi, 3.14, and however far you want to go, and it will determine from what you gave it what kind of variable we're going to store it in at that point in time.
Yeah.
It's beautiful.
So that's the end of our little video here on variables and data types in basic math functions. Brian, you have anything else to add?
Visual Basic sucks.
See you guys in the next video.
This video is going to be about binary code. So
Or, for those of you that speak binary, 011001001001001.
Oh. So binary code seems like a unapproachable, insane, foreign thing that only machines can understand.
Yes.
But not today. Today you will also understand binary code.
Yes. Yeah, so get excited, people, because binary is a very abstract thing that a lot of people don't know about, even when they work in computers. So what is binary code? Well, it's simply just a base 2 coded language. It's not even really a language, it's a numbering system that's a base 2, where we have 2 digits, 0 and 1, where 0 represents off and 1 represents on. And we can use binary to express anything. Numbers, characters, instructions.
Our number system, as you're used to, is a base 10.
Right.
So we go 1 through 10 and then start over, whatever, everything in increments of 10. Actually 0 through 9. And then 10 is 1 with a 0 through 9. And 20 is 2 with 0 through 9, and so on. And we use that because it's convenient, because we have 10 fingers.
Right.
And it was easy a long time ago for us to count in increments. So we can, have 5 on a hand, 10 on both hands, and then how many times that is. 10, 20, 30, whatever. So as a matter of convenience for us, really a base 12 is a more efficient mathematical numbering system to use, where we would go 1 through 12, 1 through 12. But 10 is convenient for us. For computers, because they're on-off switches, base 2 is the most convenient. So things, as far as a computer understands, is either on or off. So if we take our number system down to a base 2, we just go 0 to 1, and then we start over 0 to 1, 1 with a 0 to 1, and so on, just like our 1 to 10 system.
And it kind of dates back to the original non-digital computers where we were using vacuum tubes to store data.
Right.
So we would just have series of tubes that were either lit or not lit.
Yep.
And that represented an instruction, or that represented a number stored in computer memory.
Right. So now we're going to look at units of measurement for binary numbers. So if one binary number is a bit, then 4 bits is 1 nibble. 2 nibbles is a byte. And bytes are usually the units that you'll find more common in computers.
Right.
So a lot of times with computers, you won't measure things in nibbles because it's not really practical. I mean, you have a text file that's 4 million nibbles, it would just be sort of arbitrary. But a text file might be like 5 bytes,
And the reason why that's more common is in the earlier stages of computers, we had 8-bit numbering systems.
Right.
Because a nibble, you can only store up to the number 15, which only gives you 15 individual combinations, which is not that usable.
Right. Every byte is 8 bits. You also have a kilobyte. So one of those is 1024 bytes. And then a megabyte is 1024 kilobytes. And you start seeing this pattern of 1024, 1024. And then megabytes, gigabytes, terabytes. So when you go to look at a hard drive, that's a 80 gigabyte hard drive, or a 5 terabyte hard drive, or a 30 terabyte hard drive, you can see that 1 terabyte is 1024 gigabytes.
Which is 1,048,576 megabytes.
Right. So that means on a 1 terabyte hard drive, we have that crazy number on the bottom left, number of locations on the disk, on that 1 terabyte disk, that can either be on or off, times 4.
Can you actually, what number is that? That is, alright, we got million, billion, it's trillion. That's 8,796,093,022,208 bits. Think about how big that number is!
So that's how many are on a 1 terabyte hard drive.
That's like the United States debt right there.
So when you go to the store to buy a terabyte hard drive for $80 and you complain that it's too expensive, you're out of your mind. That's an amazing technical feat that we can have that many locations on a little platter that fits in your phone. That's crazy. It's massive.
There was like one point where it was obscene to think about, you need more than 200 kilobytes? No. You're crazy.
I couldn't imagine this
I couldn't imagine this situation. Oh, I wonder if that's where that came from.
I think it was with Bill Gates and the memory limitations of Windows 3.1.
So we were talking about a minute ago with 8-bit binary. Now this is a representation of 8-bit binary. Unlike in the English language where we read from left to right, computers read right to left. If you look at the blue bar on the top, look at the exponent. The exponent is 0, 1, 2, 3, 4, 5, 6, and 7. So we have 8 values. And the base number in every single one of these is 2. Thus, it's a base 2 numbering system. So we go 2 to the power of 0, which is 1, 2 to the power of 1, which is 2, and all the way up until we get to 2 to the power of 7, which is 128. So these are the individual values that we can have in 8-bit binary. The addition of all these values equals the maximum number that we can store with an 8-bit binary number. Let's take a look at a binary number. For those of you that speak binary, 00011001, which of course you all know what that meant, right? Now, Brian and I were just talking about how binary is simply an on or off switch. When I take this binary number and I append it to that box that we had in the previous slide, you can see that 16, 8, and 1 are all on, and everything else is off. So when I flip to the next slide, you'll see that 16, on this very bottom line, we have 16, 8, and 1. All the other numbers are turned off so they don't pass through. So everything that is turned on will pass through and be added to get to the decimal that this represents. So 16 plus 8 plus 1, this binary number is 25. This is 4-bit binary, which you all know now is a nibble. This isn't a byte, this is half a byte, which is a nibble. We're counting from 0 to 15. Now, we're not going to go over this slide. You can pause it and review it at your leisure. But this is counting from binary from 0 to 15. It's a fun exercise. Do this on a piece of paper. You'll have a blast. Here is the opposite, Brian. Let's take a number and let's convert that into binary.
Awesome.
Yes. Now, this is a basic modulus operation. Now, we're not going to use modulus in this example because some people may not know what that is, but I think if you've gotten this far, you should know what division is. And you should know what a remainder is. Mm-hmm. And that's really all that we're trying to get across here. So let's take this number 21, Brian. Now let's take 21 and divide it by 2. What happens?
We get 10.5.
10.5?
So we have a remainder.
We have a remainder because we have a 0.5.
Right.
So what does that mean, Brian?
That means we have a binary bit.
We have an on bit. Woohoo!
So don't think too much about why we're doing this. This is a shortcut technique for converting integer to binary.
Exactly.
So bear with us and you'll understand.
Now the next number is 10. Now where do we get 10? Well, 10 is the whole number of 10.5. So whatever the division is in the previous step, we drop the remainder and take the whole number. So now we perform this exact same operation with the number 10. So 10 divided by 2 divides evenly. So there is no remainder.
Right, just 5.
So now what happens, Brian?
So now we have no binary bit.
Oh, man, I thought this was getting fun.
And then the 5 carries down to the next current number.
Now what happens?
Now we divide it again. Now we have 2.5.
Oh, goodness.
Since we have a remainder, the remainder goes over to the binary bit is on, and we drop the 2 down.
Oh, goodness. Now this divides evenly.
Yep.
So
no binary
0.
bit. Drop the 1 down. 1 divided by 2. We have a half. There's a remainder.
Yep, so that's on. Now, here's the key. Once we get to 0, meaning when we do our division and the value is 0, we're done. I mean, technically not. You could go 0 to infinity because these numbers don't count, but practically you're done at this point. Here's our number in binary. Here's 21 in binary.
Just like everything else, we're kind of writing it backwards from what would be intuitive. So we write it from right to left as we go top down.
Yeah, so once we get this bit value, we have from top to bottom, we have 101010. We actually read that from bottom up to get the binary value.
Right.
So it's going to be 010101. Now, how can we prove, Brian, that this is actually 21 in binary?
Well, let's put it back on our chart to convert it back to a decimal number.
That is a spectacular idea.
So based on this number, we have the on position in the 0 position, the 2 position, the 4 position, and everything else is off.
So 16, 17, 18, 19, 20, 21. We have successfully converted 21 to binary and back to a decimal. Here's just another example. We're not going to spend too much time on this, but here's taking 47, converting that to a binary number, and converting it back. So this is just another example of converting a number from a decimal to binary, from a binary back to a decimal.
So now we'll take a look at hexadecimal. So what is hexadecimal? You'll hear this a lot in computer terms. You'll hear it a lot in graphic design terms. Hexadecimal numbers represent colors often. You'll see it used in cryptography. You'll see it used all over the place. So hexadecimal is a base 16 number system. Ours is base 10. Binary is base 2. Hex is base 16. A lot of times this is used to represent a binary string. We can take a nibble into a number between 0 and 9, or a character between A and F. Because 0 through 9 doesn't have any other symbols to represent 10, 11, and 12 to repeat, we're going to start using letters. So in order to get 16 numbers in a set that we can repeat, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And that's our 16 symbols that we use to express the set that's hexadecimal. Usually hex, when it's written, is prefixed with a lowercase x to denote that it's hex. You can see XFF is X 1515, or X0B is X011.
Here's a list of the valid hex values. So like Brian said, 0 through 9 represents what they are, 0 through 9. And then A through F represents 10 through 15. Here's an example of how to convert a binary number into hex. So what we're doing here is we're taking an 8-bit binary string, and we're splitting it in half. The first 4 bits, or the first nibble, goes over here, and the second nibble goes over here. So let's take 0110 and convert that to a number, and this equals 6. Now let's take 1110, convert that to a number, and that's 14. So when we combine these two numbers, 6 is between 0 and 9, so it retains its numerical value. However, 14 is above 9, it must be assigned a character value, which is E. So the outcome of this conversion will be 6E or X6E.
Done. It was that straightforward.
Yes.
Now you can convert it to hex.
And here's just another example where we take a nibble that is all on. So in 4 bits, 15 is the highest value. So you can see where that F comes from, because nothing can be higher than F. So in this case, we have 15, we have 11, F and B, or XFB. So, Brian, how do we take a hexadecimal value and convert that into binary?
Alright, well, just like a squirrel breaking down its problems into small little acorns that it can store away, we will similarly break down this problem in small little acorns.
Okay.
I don't know why I said that. 6E. The 6E is just a 6 and an E. E's value is 14. Let's convert 6 to binary, then we'll convert 14 to binary, and we'll reconstruct it into our 8-bit string. So we take a look at 6, and we go through the technique that we went through before. We start with 6, divided by 2, there's no remainder, it's off. We drop the 3 down. Divide 3 by 2, we have a remainder, it's on. And so on. 1 is on, 0 is off. And we do the same thing with 14. 14 divided by 2 is 7, there's no remainder, it's 0. 7 divided by 2 is an odd number, so it has a remainder, it's 1. Odd number, it's 1. Odd number, it's 1. Even number, it's 0. When we write out the binary, we write it out bottom up. So 6 becomes 0110, 14 becomes 01110, but we drop the leading left 0.
The reason why is because we can only have 4 bits.
Right, and it doesn't affect our positional value. When you convert from hexadecimal to binary, if you have more than 4 positions, it will always be 0. So that last one will always be a 0. So that gives us 1110.
Now let's take that other example, FB. We take F, convert that to 15, B, convert that to 11, because we just know that those are the values. And we do that process that Brian explained, and we convert 15 to binary, which is all ones. Then 11 to binary, which when we read from the bottom up on that chart there, it's 1, 0, 1, 1. So now we have successfully converted this to binary.
Easy.
And if you wanted to get the decimal representation, take this and plug it into that chart, that binary number, and now you have the decimal or the integer that represents.
Absolutely. This now allows you to go from a decimal number to a binary and back to hexadecimal to back to binary, up and back every which way you could possibly want. So you should have no hesitation being able to walk into a room full of robots and say 01101111100. Because this will be important in the future. when all the humans are dead. And there's only one kind of dance.
The robot. The robo boogie.
Oh, and the robot. That too, also.
So thanks for watching, gang. We'll see you guys in the next one.
Welcome to the introduction to ASCII. In case you've ever wondered what ASCII is, that's what this video is for.
Yes.
So, ASCII is basically plain text. So anytime you see text on a computer, you're looking at ASCII standardized text.
And ASCII stands for the American Standard Code for Information Interchange. Now, ASCII was actually compiled by like a Jedi Knight group of people that got together to decide how this should all be set up and that kind of stuff. It's essentially just an ordering scheme that organizes characters into a numerical arrangement. We were talking before about binary, and you'll notice here that we have values from 0 to 127 and 128 to 255. Since 255 is the maximum value, we can say that ASCII, at least standard ASCII, is an 8-bit character scheme.
Right.
Where characters can only be from 0 to 255. This is a standard ASCII chart that we are referencing from lookuptables.com.
So as you can see on the chart, every character in the alphabet, every uppercase character, every lowercase character, is equal to a number.
And as we go through here, we can see some special characters that are also called non-printable characters, but technically that's not true because new lines are, you actually see a new line in a text document. But these are your special characters, and this is also an alternative way of representing some special characters. So \R is our character turn. \N is typically a new line feed. We have our tab character, the bell, which is kind of cool.
Yeah.
So if you're writing a program and you want your computer to go beep, that symbol actually makes a beeping sound. Form feed, which is separating pages. Vertical tab, backspace, and null.
And you can see some of the behaviors of these tie back to typewriters or the old form feed printers, where when you're using a typewriter, you have a carriage return that'll slide the typing carriage back to the left. You have your new line feed, which feeds a new line. A new page form feed is that other button you hit on the typewriter that jumps to the next page. So it's very similar to how that functions.
We also could see that we have this arrangement of numerical characters in this sequence from 48 to 57, and our capital letters from 65 to 90. And over here we have our lowercase letters from 97 to 122. So the important thing to kind of realize from this is that in this hierarchy, you can see that numbers have precedence over capital letters, and capital letters have precedence over lowercase letters. So if we were to alphabetize a string, those words containing capital letters in the beginning will be higher in the list than the ones that don't.
And obviously, as you can see, the numeric value on your keyboard, the number 9 on your keyboard, is not actually the value 9 on your computer.
Yeah.
It's really just the character that looks like our number 9. So the computer will always interpret everything as a number.
Yep, absolutely. We want to go on an exercise here. We'll retake Whippet.net, and we kind of run through this ASCII chart, store the values, and convert it to binary. So if you wanted to get a Whippet.net tattoo in binary on your arm, you can use this tutorial to do that.
Sounds like fun.
So first we're going to get the capital W, which is ASCII decimal number 87. Then the lowercase I. Now, as this chart dictates, if you look to the left, the capital I has a completely different value than the lowercase I. So it's very different. So the lowercase I will have 105, and then the capital B, 66, and the lowercase I again, 105, followed by the lowercase t, which is 116. The period character, 46. The N character, 110, and the E, 101, and lastly, T, which is 116.
And now we'll convert that to binary.
So the next thing, like Brian just said, is we'll go through character for character and make an 8-bit binary string for each character. So WIBIT.net equals these numbers, which equals these binary strings, which when we concatenate, that's what your computer sees when you write Whippet.net in a text editor.
So as an exercise, you can try this with your name.
Mm-hmm.
So you can see your name in binary as the computer understands it.
Yes.
So this brings up the concept of a string. So when we use a string in a program, which is a sequence of characters, we can see what the computer understands that string to be, which is a collection of these numerical ASCII values. So now let's take a look at the examples. So the first one is a string as denoted by the beginning and the ending of double quotes, and in that is a sequence of characters. So you have hello, exclamation point character, space character, capital H character, lowercase o character, how are you today, what a lovely day to program. Then we can also see these special characters. So in the second example, we have a line feed. When this string is printed to a console or to a screen, it'll print, this is the first line, and then it'll get to character \hex 0a, which is the new line, or the line feed.
Which is decimal 10, which is where that hex value comes from.
Right. And then it'll start printing on the next line, this is the second line.
Now, one thing to also keep in mind is these hex values are a direct relationship to its numerical and its binary value.
Absolutely.
So when before we were talking about converting a binary value to hex, we showed you that 10 equals A. But we're talking about an 8-bit number, so we have to prefix any single value with the 0 to make it an 8-bit binary value. So that's why this is \x 0a instead of \xa.
And then in the next example, we have a hex 0d character followed by a hex 0a character. So the ASCII value of hex 0d is decimal value 13 or character carriage return. So when a screen gets this character to display, it'll take it as a carriage return and then followed by a new line feed. This is the way Windows handles new lines. Windows expects a carriage return followed by a new line to move to the second line. In our last example, there's a form feed character. So this can either be a \f in some programming languages, or it's a \hex 0c, the form feed character. So in this example, we would have, this is page 1, form feed character would take us to a new page. This is page 2, form feed character, to this is page 3.
And sort of like Brian alluded to, this is another way of representing these values. So the new line character, which is hex value x0a, can also be expressed as \n. And just like we were talking about with the Windows new lines, you typically see \r/n in Windows new lines, and the form feed is \f. So these are just alternative ways of printing the same characters.
And that's all there is to it.
That's basically it.
There's a lot of websites that have the ASCII chart. It's probably a good thing for you to bookmark. I would try a website like lookuptable.com and use it as a quick reference guide if you ever need to know the numerical values of a character on a keyboard.
Hello and welcome to the Wibbit.net video on APIs. So in this video, what we're going to do is just basically give you a high-level overview of what an API is, how it works with software development, and then a couple of examples of APIs that are currently used in today's development world. So Brian, tell me what an API is.
An API is an application program interface. It's essentially software that's written so that you can interact with other software. It's language independent. It basically allows you to extend the functionality of how you interact with an application by allowing you as a developer to code against exposed components of the software that you want to work with.
Some types of APIs are external libraries such as DLLs. There's also other objects like COM and ActiveX, which are installed on the computer that's running the software, and web services, which are remote APIs.
In the case of external libraries, this would be an executable file that contains importable instructions. This can be imported into a program to inherit functionality. So this would be something like a DLL on a computer that can be consumed by a program that you're writing, for example, so that you can acquire that functionality into your program.
And we're not going to really get too deep into this, but later on when we start writing libraries, you'll see how this works. So basically when you write a DLL program, which is a class program, you basically just define interfaces that are publicly available to external software. They're also formatted in such a way that when you import the DLL, you can specify which internal functions that you want to use, and then the software will just go out and get them and start creating the instances and objects that are associated with that. So next we'll talk about COM, which is Component Object Model. Now COM is used in so many different ways, it's really kind of hard to pinpoint every single way to use it, but just kind of as a general overview, it's a language-independent method of sharing objects. Typically, COM objects are something that are installed on a computer. A really good example of a COM object is when you install Microsoft Office or when you install OpenOffice, it throws some libraries on your computer that you can use programmatically create Excel spreadsheets or Word documents, or even use, like for example, the OpenOffice API. You can use its ability to convert Word documents into PDFs in your own programs just by simply installing OpenOffice on the computer.
So in the case of Microsoft Office, a Word document is essentially an object model. The Word document itself is represented within the COM object as an object. Part of that object has functionality like make the font bold, make the font a certain size at a certain location, add a page, save the file as something on the file system.
Convert the file to something.
Right.
Yep.
So all of those functions and all that functionality is written into the object model of a Word document. So when you write a program, let's say it's in Perl or in any language, and you create an instance of that object in your program, you can call those functions to save that file you're working with and write to that file through your program.
The QFTP API, I mentioned this because I think it's kind of cool. Like, it allows you to easily access like SFTP and FTPS stuff, so you can just throw that in your program without having to write any of that yourself.
ActiveX is similar to COM, but it utilizes OLE, or OLE, Object Linking and Embedding. OLE is a technology that embeds a document into another object, or an object in an object. So for example, in rich text files, a long time ago, you would commonly see it by putting a bitmap in the rich text file. It would be a form of using OLE. So instead of the rich text file format knowing how to support and display a bitmap, it's leveraging other functionality that the system understands to display the bitmap. This is used in a lot of other ways today still.
Yeah, like so a lot of websites will use ActiveX controls, and you'll know it too because when you go to a website, like when you go to like WebEx or those types of websites where you're sharing your desktop, that's an ActiveX object. When you go to the website and you haven't been there before, it's going to pop up and say, you need to install this control to use this website. And what they're actually doing is installing a piece of software on your computer that the HTML document embeds within itself. So this whole embedding a document inside of an object, if you look at the HTML code has an object type of, and then it actually calls the ActiveX control from the HTML document to embed it inside that program.
Right, which is effectively asking your computer how to handle that file format. Mm-hmm. And since the ActiveX control installed that library on your system, now your system knows how to use it. Which is also why ActiveX is not necessarily the most secure means of doing things over the internet.
ActiveX has been under scrutiny over the last, 8 years or something like that.
Because it's effectively, by way of a browser, allowing you to install directly into your COM layer of your operating system.
Yeah. It's also a good way for transmitting viruses and that kind of stuff as well. Yeah. So when you accept an ActiveX control, be sure that you trust the source that it's coming from. So next we're going to talk about web services. It's basically just using URLs and a method of posting data to a web server to retrieve either text, XML, or binary data as a result that's inserted into a program. Now, you can use web services in so many ways. I mean, there's tons of ways you can use them. You can import them as references into programs. You can have a program that has a piece of code that actually sends data to a web service. Like, there's just so many different ways that you can use a web service. Like in today's world, simple things like getting a stock quote you can use as a web service. You can even send a document to a web service and have it respond with a different type of document for conversions. I mean, there's just so many ways you can use them.
And as mobile applications become more popular, web services also become more popular. If you put all of your functionality of an application in a web service, the only thing that you have to develop on a mobile device is the front end for it.
Yep.
So the front end is just a basic user interface with which to access the data that's provided by a web service.
And as Brian made a really good point that web services, Brian and I, we're both in the field. We see this are on a huge growth right now. The demand for web services is very high. And like Brian just mentioned, you don't really have to put too much work into expanding your application into other platforms because there is that centralized processing model, which is the service that provides the data.
So here are a few API examples. One is the Google Maps API. So if you have a website and you want to embed a Google map into your website, you're essentially calling the Google Map API in order to do that. Another one is the Adobe Acrobat API. A lot of people do this for the creation and displays of PDFs and other programs. So if you write a program and within it you want to display some informational PDFs, then you might call the Adobe Acrobat API and as a requirement force the user to install something like Adobe Reader before they install your program so that you can leverage the Adobe Reader functionality of displaying the PDF in your program. Another one is Microsoft Office, like we were talking before, if you want to programmatically generate Excel files or if you want to programmatically fill out Word documents. Other API examples is applications that use embedded Flickr streams, or the Facebook API examples are like the throw a Hillary Clinton at somebody on Facebook applications or like Bejeweled, all leverage the Facebook API.
There's one that we don't have on this list that I want to mention because I love it, and that's the GoScript API.
Oh, yeah.
For those guys out there that are doing document manipulation, nothing's better.
Absolutely. Hello and welcome to our video on IPC, or Inter-Process Communication. The IPC is essentially how two programs can communicate with each other. So we're going to look at the different ways of performing inter-process communication, and when it's used and why we would use it.
The first thing that we want to talk about right off the bat here is what is a process? A process is nothing more than an instance of a currently executing program. If you take a look at our little thing down here, we have our little computer that's controlling a application called program.exe, and that is the process. Now there's another side of this, and that's a thread.
And what is a thread? A thread is the result of a program forking a currently executing program into two or more concurrent tasks. A program will have tasks that need to execute independently, so those tasks can occur, many of them at the same time. So a program will generate many threads to execute tasks. And this process is basically called forking, the spawning out of child subprocesses called threads.
One thing that's really important to understand about forking and about threads is that this wasn't always there. This is something that kind of came along once computers began to multitask and you could run more than one thing at a time. Because what you can essentially do is take one program and have that one program spawn out into many different types of tasks. Like, for example, a socket a lot of times is running as a thread. Because if you don't run a socket as a thread, then your program is stuck in an infinite loop of listening and it can't do anything else. So what you would do in that instance is you would make a program that spawns off a thread, and then your program then jumps off and does something else while the thread sits there and listens.
Right. So a very basic example of this is if you had a web browser. And every time you click a link, from the time you click the link until the time the web page is fully downloaded, your browser would freeze.
Or your computer.
Or your whole computer would freeze. You couldn't move your mouse, you couldn't do anything. You'd just sit until it fully acquired the response from the website, and then it would continue.
So let's kind of talk about this inter-process communication thing. Brian kind of gave a little bit of an overview in the beginning, but it's really a method used in software development to allow processes running on the same or different computers to communicate with each other. And here are some of the basic methods of inter-process communications.
So we have a file as a means to communicate between processes, a database, a signal or an event, or a network socket. So in the case of the file, we have multiple processes and threads that all refer to the file system to send messages to each other. So as you can see in this example, we spawn off program 1, and program 1 writes to file.txt. Then program 2 reads from file.txt. So now what program 1 has delivered to the text file, program 2 has read from it. This also works in a larger sense in Linux operating systems, where a lot of the information of the operating system's status is stored in a virtual file system. A lot of times in Linux you use a file method for inter-process communication, but they're not actually files the way that they would be in Windows. The files don't necessarily exist. It's sort of a virtual file system.
I think that's called the proc file system.
The proc file system, exactly. And it's a lot faster than reading and writing from the hard drive.
Next, we're going to take a look at databases. So multiple processes can share information based on a single point of data storage. Now, you could make an argument that this definition fits a file. And you could technically be correct because, you know, from a technical sense, a text file can be a database. Technically.
Yeah.
But the difference here is...
so can a hard drive.
That's true. That's true. But the technical difference here is that a database uses a database management system, which is usually a piece of software that is a layer that runs on top of the database that controls grabbing, storing. It also controls simple things like locking of the database, and if multiple things are coming in at one time, it controls that flow. So there's more intelligence in a database than with just a regular text file. So here's an example, and it's very much like the file example. It's just that we're pulling from a database. So the computer spawns program 1 and program 2, and program 1 sends something to a database, and program 2 retrieves something from that database. So effectively, these two programs were able to communicate by using the database as an intermediary. There's also a different database communication model, and this is a remote database.
This is similar to our last example, but the database is not on a local file system. So let's walk through this. The computer on the far left executes program 1, so that program1.exe is now running as a process. That process will send a request through something like the internet or a network or whatever, some unknown system, which finally makes it to database service.exe, which is a process running on another computer. That database service.exe is running on a server that communicates to the database. So the request from program 1 goes through the cloud to db service.exe and writes to the database. Now another computer, executing program 2, sends a request through a different cloud or network or internet or anything to the server, to db service.exe, sends the request, is written and processed to on the database, and a response is set from the server, db service.exe, back to the requesting system. This is effectively the same way that the two programs access a file, or the two programs access the database, but instead of having the operating system manage how to access the file, it's another computer considered to be a server somewhere else on a network.
So when you have your phone app that checks the weather for you, this is what's happening.
Absolutely.
Your phone app is going to a database and just pulling data, but that data gets sent there by the local weather systems from the different cities that are reporting the weather. The next form of IPCs that we're going to talk about is a signal. A signal is really nothing more than a message that is sent to a process to notify it that an event has occurred. This also fits in with the concept of interrupts. An interrupt signal is sent to the program, which means when an interrupt signal comes in, it stops doing what it's doing. So everything that it's doing, it says, whoa, whoa, stop, stop, signal's coming in. Then it takes the signal and interprets it before it continues, whatever that signal will be. Now, for a lot of you guys, you'll be most familiar with the SIGINT signal, which we know as the control break or control C sequence. This is a sequence or a signal that's used to terminate a process. So when you write a program and it's running, or when you're running a program from a command terminal and you do control C, the program will just kill. Control Z is a similar type of thing, except for it doesn't kill the process, it pauses the process.
So another type of inter-process communication method, which is similar to a signal, is an event. The difference between a signal and an event is that an event does not necessarily interrupt the flow of the executing program, but that request is still queued up and can be accessed by the program. Common examples of an event is a mouse click or mouse movement, keyboard buttons being pressed, a new file being created, a TCP message received on your network card, or mouse hover over. So in these cases, you have an event that happens. That event happens regardless of where the program is running and what state that program's running in. When the program gets to a point where it wants to know what events are pending, it will go and ask and find out what events have happened and handle them accordingly. Here's an example of an IPC method with a network socket.
Now, this kind of differs from the database example in a very fundamental way, because there's no intermediary. What's happening here is we're sending a transmission over some sort of a network protocol like TCP, IP, and we're sending a message to a server program that will respond back to you with a response. So in this example, our computer is running client.exe, and we're going to send a message to server.exe that's asking, how much money is in my account? So we're checking our bank account. Now, server.exe does what it has to do to get the information, and it tells Brian that he has 37 cents in his account.
Which is great, because that means I didn't overdraft.
And that's the most money I think you've ever had in your account
Probably.
at one time.
So thanks for watching.
Well, before we start talking about this presentation, Brian and I would like to thank you for bull-moosing your way through all this material and getting to our last introduction video. In the beginning, remember how we asked, am I a software developer? If you've gone this far, chances are you've got what it takes.
Or you're obsessive compulsive, and you need to see more of this blue gradient.
Maybe you're just obsessed with the gradient background. So the last thing that we want to talk about in our introduction series is bitwise operations. I'd like to say that we saved the best for last, but we certainly did not. Bitwise operations are not fun, but they're very important to understand.
Mm-hmm. So we can basically break down the bitwise operations into just a few simple statements that all logical operations are founded on. It's either an and, an or, an exclusive or not.
Let's talk about a bitwise and. A bitwise and is simply two binary strings of equal length. We perform a logical and operation on each pair. So what is a logical and operation? Well, if both values are 1, then the output is 1. Else the output is 0. Thus, it has to be on yes and yes for it to be true. So it has to be this and this, then it equals true. So let's take a look at an example. If we take a look at these top two binary strings, and we do a logical AND operation on both, let's go from right to left because that's how the computer reads this. We see that 1 and 1 are both on, therefore the value is 1. 1 and 0, well, they're not both on, it's false. 0 and 0, neither one of them are on, it's false. Again with 1 and 0, false. Again we see 1 and 1, that's true. The other ones from the next three over are going to be false because we have different combinations or we have two off bits.
So we can see a 1 is a statement of truth and 0 is a false statement. 1, it's true. 0, it's false. You have to be true and true. If it's true and false, that's not going to work. It has to be true and true. Now we'll look at the bitwise OR operation. Similar to the AND operation, we have two binary strings of equal length, and we can perform a logical OR operation on each pair. With the OR statement, if at least one value is 1, or if at least one value is true, then the output will be true. Otherwise, the output will be false or 0. So if we look at this example, and we run from right to left, we can see that if it's true or it's true, it's true. If it's true or false, it's still true. If it's false or false, neither were true. So it's false. So 0, 0 is 0. And we can carry all the way to the far left and see 1 and 0 is 1. So if at least one of the two are on and the other is a 0, or if both are on, either will fit the criteria and they will be true.
I also want to take the opportunity, looking at these two binary strings, to kind of explain what we mean by binary strings of equal length. Technically speaking, the bottom binary string is not the same length as the top. Because from left to right, it would read 1, 1, 0, 0, 0, 1. In order for us to do a logical operation on this, we have to make sure that both binary strings are of equal length. So whichever binary string is shorter, meaning wherever the last 1 is in the bit, we take the second binary string and we append zeros to the left until the length are the same. Because with binary, it doesn't matter how many zeros you append to the left because they don't count. They're all off. So this is an example of how we did that to do this comparison. So the next one we have the bitwise exclusive OR. So we take our two binary strings, we perform an exclusive OR operation on each pair. Now the difference between OR and exclusive OR is both values must be different. In the OR operation, 1 or 1 is true. But an exclusive OR, 1 or 1 is false because it needs to be two different values. That's why they call it exclusive OR. So here's an example of that. Before, when we did the OR operation, the far right bit sequence was true. 1 or 1 was true, but since now we're looking at it exclusively, 1 or 1 is false. So any situation where we have 1 and 0, they're true, and every other condition is false.
And lastly, we have the bitwise NOT operation. So this is performed on one binary string, and is not necessarily a comparison of two, and it's a logical NOT operation. So if the value is 1, the output is 0. Otherwise, the output is 1. So the result will always be the opposite of the statement of truth.
Exactly.
So if we look on the far right, If it's not true, it's false. If it's not false, it's true. And so on all the way through.
Exactly. So the binary string on the bottom is the complete opposite, which is the not.
Right. And that's a very fast crash course in bitwise operations.
Yes, so this concludes the Introduction to Programming tutorial series. So thank you very much for watching.
And congratulations for making it this far.
We'll see you guys in the next tutorial.